Fissured, one of the second councils under the Department of Science and Technology. We are all about innovation and progress. We lead and partner with public and private institutions in generating science and technology policies, strategies, and technologies that spur national economic development. We formulate policies and strategies for scientific and technological directions. We fund and support R&D efforts in the industry, energy, and emerging technology sectors. We provide opportunities that enrich human resources and facilitate the development of institutions. We move technology forward through adoption, transfer, and commercialization of available technologies. We ensure timely and effective delivery of research results. The Council encompasses sectors under these priority areas. And all of these are backed by a highly skilled and science technology workforce for quality technologies and innovations. We are driven in bringing homegrown science and technology to the fore of the competitive global arena, creating impact on the country's progress and improving the quality of life of every Filipino. We uplift lives through innovation. Be sure, we are the Innovation Council for Industry, Energy, and Emerging Technologies.
Since I started working in UP way back in 2012, DOST has been very helpful, and it has been a huge factor in my being able to put up a modest terahertz research and development laboratory at the National Institute of Physics. I have been receiving funding through research grants and travel support from the DOST Fissured since 2015, and up to now I have a program that has been ongoing for the past 3 years.
Good morning, world. Good morning, Cebu. Welcome to the final day of the 2025 Quantum Information Science and Technology Conference in the Philippines. We have had two incredible days of discovery, collaboration, and vision. By the way, I am Jess Quinas Cathedral from the University of the Philippines, Cebu.
That's right. In day one, through our esteemed speakers, we explore quantum hardware, investment opportunities, and security applications. We also had a banquet dinner by the beach. I'm sure you guys had fun. I'm Dani Spanyola from Chongyan Christian University, Taiwan, co-hosting with Keen this morning. Good morning, Keen, and good morning, everyone.
Yesterday, we had a series of talks and panel discussions, and in the afternoon, everyone participated in the quantum diplomacy game, which highlighted one thing: collaboration. It is the key to a responsible quantum future. And to give the synthesis of the quantum diplomacy game, may we call on Dr. Marian T. Skorchain. Once again, may we call on Dr. Marian T. Skorchain to give the synthesis of the quantum diplomacy game.
something that if you talk about complex diplomatic relationships
Okay,
between
thank you,
countries,
Nayan. Thus we will
it plays a decisive role as well. So all in all, I think I hope you will also get to exchange with people within your groups, but also with other groups on the different kinds of points that really stuck to you about the game, and that you will also confidently go forward thinking about the parts that you would, in your own real life discussions, that you would want to revise to really come to actionable solutions quickly. And the working groups today may be one format in which we test a different approach to actually finding solutions that we carry forward. So with this, I hope we can wrap up the game nicely, and we can have follow-on discussions in all the breaks that we make. Thank you very much for participating and for taking the time and the energy.
So, thank you, Dr. Rufra. So,
Today it's all about research, regional collaboration, and regional cooperation, and charting the path forward. And to open for today's event, we welcome the Associate Professor from the University of Queensland. She leads QISTCon at UQ, pioneering research in high-dimensional quantum systems to push the frontiers of quantum information science and future technologies. Let's welcome with a big hand, Dr. Mary Jacqueline Romero.
Good morning, everyone. Thanks for coming. I'm very happy to be here. It's my first quantum conference in the Philippines. Could I have my slides? My slides. Okay. Oh, great. Okay. So when Bobby asked me to come here, the first request was to talk about women in quantum. But I thought that's not a problem here in the Philippines because actually we have a lot of women in physics and women in quantum physics. I think from this conference you could see we are at about 30%. If you look at the American Physical Society Division of Quantum Information, that would be optimistically around 10%. So I think that's something that we have to take advantage of here. I'm going to talk about frontiers in quantum research. That was the ask. But I want to come here as a physicist. So I want to talk about what is quantum in the year of quantum and really just what I find interesting. So I hope you will humor me and listen for the next 30 minutes or so. Before I begin, I'm going to thank my sponsors. My research has been funded by the Australian Research Council and Westpac Bank, which is one of the 4 largest banks in Australia. So if there's any banking people here, let that be a lesson to us. And of course, L'Oreal UNESCO Foundation for Women in Science. Okay. We've heard community said in this conference a lot of times, and this is one of the main messages I want to convey. It takes a community to raise a scientist. I am one of the scientists that has been raised here in the Philippines. I got my scholarship in Philippine Science High School many, many years ago. I'm a Y2K graduate, so I know what Y2K is. I went to the University of the Philippines. I did an applied physics and master's in physics degree. And then I went to Hogwarts in the University of Glasgow where I did research for 7 years. I am now based at the University of Queensland where I had a group called QISTCon at UQ. I'm going to talk about that in a while. That's our website, quantum@ibapa.org. At-ibapa is like the Filipino version of etc. So I talk about quantum and many other things. So the main messages I want to give in my talk is one, quantum is not magic. It's really not, it's one of the things that annoy me when I go to conferences and people say quantum and magic in one breath. We are all fascinated by magic, but we don't want to be magicians. So I important. Quantum is physics. It is just physics. Whatever trouble we have in understanding quantum is not in the physics, it's in our heads. And I think that's one of the shining moments in my career was in the opening of the quantum year in Paris, and Sir Peter Knight said just that, and and quoted me, and that's really good. And lastly, I want to say quantum is amazing, and not just quantum computing. There is a lot in quantum mechanics, and I want to talk about those things today. Now, one of the controversies, issues, whatever you want to call it, is that there is a divide between quantum physics and classical physics. You will find various positions on this question. My position is that I don't think there is a divide. There is just a useful theory and a not useful theory in any particular situation that you will encounter. And to me, quantum is like that. There is only information, and you can treat it like classical information or quantum information. It's in the way that you have information. One example that surprised us in the very beginning of the history of quantum physics is this problem, the box potential problem. When you have a particle in a box, do I have a laser pointer? When you have a particle in a box with a red dot, you ask the question, in this box with the infinite potential represented by the black lines, where will the particle be? And the classical answer to that is that it can be anywhere in the box. But in quantum mechanics, actually the answer is that, well, it can be only in where you have the amplitude. Where amplitude is not zero. So particularly where the function is zero, you will not find the particle there. And it's more likely to be where you have a lot of the wiggling, like in the nodes and the antinodes. So there you have maybe one of the differences that was discovered was that you have these questions with different answers in class. Scientists here in the Philippines that information is physical, and the rules that you apply to information really depend on the physical system that you have. So maybe the young people here would know TikTok, Facebook, Instagram, whatever. Those are information in physical systems. And you might have done this experiment yourself when you were young, the telephone using cans, and you've got the string vibrating. You hear the voice of your friend. That's one example of analog information carried by a physical system. On the bit, so we have the wavy thing that we've discretized into the 0 and 1, and that's the basis of our classical information, 0 and 1. The bit, which is the simplest classical system, heads or tails. And here in quantum information, we've got what we call the qubits, so spin plus 1 minus 1. If you want to think of a physical system, you could think about the way that the electron is spinning. So that's our qubit. Where should I be pointing this thing? Okay, qubits. Okay, and what's so special about qubits is that, one, there is no way to measure a qubit without affecting its state. And this is, the measurement problem in quantum mechanics, which up to now is, undecided, very active debate. Mathematically, qubits are represented by a different mathematical object, and they are represented by complex numbers. Raise your hands if you know what a complex number is. Great, okay, because all this time has been just leading to this. So complex numbers, they have a real and imaginary part, just like life. Okay, that's your first joke for today. We have real and imaginary parts, and really, to me, that's the difference. You have complex numbers with interference that you can control using your physics instruments. Okay. I started in quantum by Googling quantum because I heard my physics teacher complain about quantum. That was a long journey because there are a lot of articles that are actually not correct. Recently, I have found this book, Quantum Mechanics, the Theoretical Minimum. So if you want to have a go at quantum, I'd really encourage you to read that. I will not have time to talk about entanglement, but we're probably familiar about it. And if you are a professor teaching quantum mechanics, I just show you here where quantum mechanics starts, usually the hydrogen atom energy level, and strongly discourage you to start from that because that is really boring. Entanglement is where we should start. Okay, we have heard a lot about quantum technologies, so I will not talk about this a lot. I just picked some experiments that I thought are remarkable and to me as a physicist was very impressive. So the first one was the quantum key distribution intercontinental. So intercontinental between Europe and China back in 2017. This was ground station to satellite and back. That was the most secure video call back in 2017 at kilobyte per second rate. That's Anton Zeilinger there at the right. He's a Nobel winner. But more recently, this experiment was even broken. The record was broken. So now our record for intercontinental quantum key distribution is at 12,900 kilometers between China and South Africa in Stellenbosch. So South Africa, Stellenbosch. I don't think you would think of South Africa as a leader in quantum physics when you look at the world, but you really can see that with willpower and expert talent in a country with other problems, you can do some really impressive things. And I hope we take inspiration from that. So what's impressive about this experiment is that they got rid of the ground stations. They have portable optical ground stations instead. So you could actually drive them in a truck or something. So you can change where your ground station would be. And instead of using the MISHUS satellite, which was a satellite commissioned by China to do quantum information in space, they use microsatellites instead. So you have a 10-factor reduction in the payload of your satellites. Maybe Spectral will do something like that. Okay. Quantum sensing. So we heard a lot about choosing problems that resonate with the community in your country. And this is one Australian example, because Australia has a lot of mining. Like it's a resources-intensive country. So one of my colleagues at the university was proposing this quantum way bridge, where they'd actually use clouds of atoms, so you'll literally, cloud of atoms, you'll ask the truck to drive by it, and with the distribution of the atoms in that device, you could have very precise measurements of the weight and the mass distribution carried by that truck. So apparently, mining companies are very interested. Okay. So now I want to talk about quantum computing, but from a very physics-cautious perspective. I think Julian really described it very accurately yesterday. Quantum computers are not just faster versions of classical computers. The provable advantages are for very specific problems. And we already know these. You've got advantage for Shor algorithm, which is factoring large numbers, and Grover algorithm, which is finding an item in an unsorted database. So when physicists talk about advantage in quantum computing, usually we refer to a scientific advantage, like a provable advantage that I can prove using theorems and all that, using complexity theory. And often we are looking for exponential speed-ups or some polynomial speed-ups. We talk about the advantage in terms of exponential, quadratic, etc. which is very different from the way that quantum advantage is used in literature these days. So, okay. So I want to share my thoughts about quantum computing in general, because I know there's a lot of work here and internationally. Quantum advantage for optimization problems are inconclusive. And when I say inconclusive, there's no provable advantage in the way that Shor and Grover has. But as Julian said, there are advantages maybe in terms of 1%, 2%, 3% improvement. So there's maybe financial advantage there. Classical algorithms are often better for convex optimization. So when you have a function with many minima, there's no proof that a quantum computer will be better there. There's a very hot area right now, which is quantum machine learning. So this is using a quantum computer to perform machine learning. Are there advantages there? And my thoughts are, and I think many quantum machine learning people agree as well, machine learning in itself, like using deep neural networks, is very hard to understand. It's a neural network. And if you're gonna claim a quantum advantage that, if you run that in a quantum computer, to me the premise is that you understand machine learning first. And that's not true. We don't understand it. So it's hard for me as a scientist to prove that running that in a quantum computer will lead to an advantage, because I don't understand this thing. So I think we just have to be cautious. It's very challenging. And this is one of when I was a 15-year-old Googling quantum, I read an article that a quantum computer can solve the traveling salesman problem efficiently. That's not correct. Traveling salesman problem is an NP hard problem. The advantages for quantum computing lies on the BQP, BPP space. So I think there's a lot of complexity theory that we need to figure out before we can claim that thing. So what am I getting at? Quantum is physics. Whether quantum computing will change the world in the next 10 years, in the next 20 years, is maybe not as relevant as using quantum physics to understand the world. And I want to go back to, what Feynman said in 1982, which started quantum computing. The world is quantum, nature is quantum. So if you have some system that's described by quantum physics, you use a quantum computer. And that's really an interesting problem and a very hard problem. And 1982, come 2000, who's heard of the DiVincenzo criteria? DiVincenzo criteria, okay, a few of us. So the DiVincenzo criteria is what do you need to make a quantum computer? So I'll give you a moment to read that while I drink some water. Okay, are we reading? There's gonna be a quiz. Okay. So, if you look at that, you can divide the criteria into 3 things. So first, you have to be able to generate your qubit and specify what state of the qubit you want. You need to be able to process that qubit in the way that gates process bits. So that's the processing part. And then you've got to have measurement and detection. The last 2 actually was not in the original DiVincenzo paper. That was added later on, but I think it's very relevant these days, because especially now we are realizing that we cannot have a useful quantum computer in one system. We are going to interconnect our chips, and that is good if you are a photonics people like me, because the most effective way of connecting chips is by using photons. I mean, that's what our quantum internet is based on. Before I go to what I actually do, I think I have 15 minutes left in my talk. I wanna talk about the difference between a matter-based and a photon-based computer, because I find when I talk to people, we have different languages because we just have very different systems. So I wanna identify what are the differences. So matter-based, example, superconducting qubits like IBM, Google, spin, ions, neutral atoms. So those are matter, they're matter. The qubits are fixed in place. You fabricate your qubits, they stay there. And then the computation happens as time-dependent controls, like signals, are fed into the system in a particular order that your physicist has computed, and then you're able to solve your problems using that. So it's very similar to a conventional silicon computer, okay? Now, a photon-based computer is different. So photon-based, there are two main examples. So photons, like psi-quantum, or measuring an electromagnetic field, like Xanadu does. Here you have pulses of light that are moving through optical fibers or waveguides. So your qubits are actually moving in your system. And you use entangled qubits to do the computation. You have to continuously create them because you are continuously measuring them. So it doesn't look like a conventional computer. It actually looks like an optical network. So when we are benchmarking a quantum computer, often we talk about how many bits do you have? How many qubits do you have? If you're a photonic person, that doesn't make much sense, because are we talking about the photons that I have generated in the whole time of the computation? It's very different. Often we talk about how quickly can we generate the entangled states. And how many entangled states we need to generate depend on what we are doing. So it's very hard to benchmark. So I mean, just be wary when we are comparing quantum computers. Now, quantum computers of both types exist. They are not useful at this time. This is one example of a use case. I did not bother to find the name of this molecule. Let's call it E32. Okay, it's got 119 atoms. And if you want to solve the configuration space of this molecule, you will find that with current 2025 technology, you will need more than a decade and 10 million upwards physical qubits in order to solve that. And in order to, what we are saying is that in order to make that economically viable, you have to be somewhere around this pink region here. And how do we get there? One, we need high-performance qubits. So when Julian said yesterday that it's an engineering problem, it is an engineering problem once you have chosen your qubit. You make your roadmap and you engineer your way to that. What I'm saying as a physicist is that you can start with a qubit that is better. If you think about high voltage will become a low voltage in a classical computer, yes. What's there? Somebody's raising their hand. What's the 10 to the minus 18? Okay, 10 to the minus 18, correct. So 10 to the minus 18, that's like the number of grains of sand on Earth. And 1 in 10 to the 18 bit will flip. Okay? It's very good, very reliable. What is the qubit error rate of the best superconducting qubit? It's, depending on who you believe, it's like 1% to 0.1%. Okay, 1 in 1,000. So we are orders in magnitude away from reliability that we have as a classical computer. So as a physicist then, my question is, well, can we find a better qubit to start with? And So you see, it's not an engineering problem to me. Another thing that we need is resource-efficient logic. The number of physical qubits that you need for a logical qubit will depend on the error correction that you have. For a long time, we thought that was the surface code, and now we're all going to LDPC. I'm not an expert, I'm just throwing these terms to you. But what I'm saying is, there is a big space for quantum error correction that I think we still need to explore. And then lastly, I don't think we have figured out how we will interconnect these computers. Like superconducting quantum computer, you control that with microwave, you have microwave photons. If you're gonna have a distributed quantum computing network, your best bet will be photons, because we already have optical fibers, we have figured out these optical infrastructure, so it makes sense to convert microwave to optical, and that's a very hard physics problem. So there is a lot of science, I think, and there's space for a lot more people to work in the field. So at UQ, we're QDITs at UQ. I'm going to talk about QDITs. QDITs. What are QDITs? So this is a qubit, 0 and 1. I use particles of light, in particular their shape. So like you think about the intensity distribution of light. That is my qubit. And the nice thing about that is that I can do dead and alive cat, but I can also do dead and alive chick, or whatever you like, because I can control and prepare different shapes of light. So I have QDITs, dual rail versus D-rail. And it's very niche, like at this point, that's the Google Trends. My group started there, so one of our tasks is to Google QDIT so that I can have graphs like this to present in talks. Qubits is like this, so you see there's a lot of work to do. But I think it's a very interesting system to work with because one, you start with a higher information capacity. If you just think about how many orthogonal states can you represent with 10 qubits, you can, if you have 10 qubits, that equivalent would be 2 32-level qubits, right? And another thing is it's more robust. Like in quantum mechanics, we do not have a quantum photocopying machine. That's the no cloning theorem. But you can do cloning if you are prepared to accept some failure. And the failure rate actually becomes higher as you go to higher dimensions. So it gives you extra robustness against that. If you're doing QKD, QDITs give you higher error thresholds. So it makes sense to use QDITs. So as a scientist, I am interested in what can be done only with QDITs and what can be done only with QDIT entanglement. Because I think I don't want to compete with, better than that, better than that. I want to do, what can you do only with QDITs? I've written articles about it. I can give you a copy of this one. I'm giving you this. It's a Lord of the Rings kind of map for entanglement in higher dimensions. I think it's really interesting. It's very different from qubit entanglement. Okay, I have 5 minutes left. Do I have 5 minutes left? Yes? Okay. So in my group, we work on transverse mode, so the shapes of photons. So that's, if you think of photons, you can think of color, the path that they take on your chip, the time that they arrive on your detector. In our group, we work with transverse modes, the photon shape, because it introduces some parallelism and maybe not as much complexity. In order to work on that, we need to design some new devices. And when I say design new devices, that's because I don't want to do this. So this is a multiplexer for transverse modes. As you can see, it's very carefully tuned so that you've got the exact width, the exact length. It's tedious. In our group, we do photonic inverse design instead. So photonic inverse design is an optimization. It's machine learning for quantum for photonic chips. It was, the package that we are using came from Stanford University from the group of Yelena Vukovic. And here, the nice thing about it is I don't start from the physics. I start from the function of the device. So say here I have a 3x3 piece of silicon, which I want to have some inputs and some particular outputs. I design a cost function for it and then let the algorithm run. And here we're trying to do a multiplexer, so like we're just TE0 and TE1, like those two shapes will go together in that one output port. And you see we have very good performance here, and we can fabricate them. This is for the physicists in the room, but maybe there's not many. So we tried this very weird-looking device in an actual quantum experiment. I will not have time to describe what the Hong-Omandel interference is. It's the hallmark quantum optics experiment from the 1980s. And we did that in our inverse design devices. We asked for some very good photons from our friends at Griffith University, and you don't have to understand the details here. What I want you to focus at is that there is a number there called the visibility, which is 99.56%. A good quantum experiment will have that as 100%. And we are able to achieve 99.56% with those inverse design devices. And we can do it reliably. So like this right figure here are just different iterations of that device, and we showed that we could actually get 99% very reliably. So I want to leave some time for questions, so I just end with this message, which I'll just reiterate. And I'm going to thank you, share you my photos of the Nobel winners from 2022. All my photos, by the way. I've met them all. I can tell you the interpretations that they favor in question time. Okay, thank you.
Thank you so much, Dr. Romero. So, are there any questions from the audience?
I promised you a question, so thank you for so casually putting D-Wave out of business in the first 10 minutes. You made me very sad. You said quantum is not magic, so I'd like to challenge you. 40 years into the future, you're probably at the end of your quantum career. What do you think is the most fun and coolest thing that quantum will have delivered by then?
So there is, can I give you two answers?
Yes, please.
Okay. One is very philosophical. Like what attracted me to this field is that you've got the philosophical tension and the really enabling technology. 40 years from now, I don't know how it will happen, but I hope we have a better idea of what interpretation of quantum mechanics is I don't know, most likely, or maybe it's figured out what interpretations of quantum physics. The other is that I really hope that quantum has changed the world. Like, I really hope that we will discover E32 and figure out today what we will do when we have E32. Because I think our only shot of discovering those catalysts for greenhouse emissions, carbon capture, is a quantum computer. I truly believe in my heart that is true, but I don't know how we get there. But maybe 40 years is enough.
Good. What's the substrate that you use on your chip?
We're using silicon at the moment, probably
28.
moving to silicon nitride, and I'm trying lithium niobate as well.
Any more questions?
Hi, thanks for the talk. I have a semi-physics question. You mentioned a lot about, you mentioned a little bit about qubits, but I feel that that's half the story because I don't believe there's free lunch in the world.
Oh yeah, exactly.
So what's are the bad things about qubits?
Yes, of course. I'm going to go to a specific example. So Psi Quantum, which is a very big photonic quantum computing company that is backed by $1 billion investment in Australia, they need to entangle photons. The entangling success of qubits is 50%. Like there are theorems, it's 50% max. you can do higher entangling probability success with QDITs. But the problem is, you have to carry that advantage all the way to the end. So meaning when you do your decoding, when you do your measurement, you have to carry that advantage. And so far, I don't think we've figured out how to do it. I don't think it's impossible, but it is a hard problem. Yeah, so that's the catch. Higher entangling probability, but maybe harder to measure it as well.
Okay, thank you so much. I think I can accommodate one more question. Anyone from the audience? Okay, so I have a question, Dr. Romero. So I think this is a controversial take. So what do you think about people saying it's not important to take up quantum mechanics in understanding quantum computing?
In order to do quantum computing, if you want to use it, design algorithms, do error correction, the maths is really not, I think you can do it without really immersing yourself in all the foundational questions of quantum mechanics. Because it's linear algebra, tensor algebra, SUD, that's all mathematics. In order to appreciate it, like to really be affected by it in maybe the way that I am, I think you need to understand it. So like I often tell my group, I am a quantum physicist, quantum engineer. I think about the foundations of quantum mechanics on weekends. Like the romantic side of it, which is also very fun. I think you need to understand that in order to appreciate it. To make something useful, you need to understand not just quantum physics, like you need to understand optics, you need to understand how waveguides work, like it's, the more you know, the better you can do. But if you just want to use it, I think maths is enough.
Thank you so much, Dr. Romero. And I think that ends our Q&A session for Dr. Romero's session. Let us give her a round of applause.
Thank you, Dr. Romero and Mr. Lance Raquel. So for the next presenter, we will explore a key piece in scalable quantum networks, quantum memory. Let's welcome on virtual floor A-star scientist, Dr. Michael Sayat.
Is my audio coming okay? Alright, awesome. So, first and foremost, I'd like to thank the organizers of the conference for And so just as a quick introduction, what is a quantum memory? It's simply a device that stores and retrieves quantum states. It's analogous to any storage device, or for example, in the classical framework, it would be a USB or a hard drive. You put in information and later on you retrieve it. Except in the quantum memory, it would be quantum states. And in these quantum states, you have the opportunity to encode information. At the same time, taking advantage of the quantum mechanical properties. And so in our lab, we're looking at 3 different metrics. First of all is the storage time. How long can we store these quantum states? The bandwidth, how many times we can use the quantum memory for a given period of time. And the operating wavelength range, which is quite important. And the efficiency. How many useful photons actually come out compared to what's being put in. And so the platform we've chosen is in rare earth iron doped crystals. There's been a lot of study in this field, mostly in this host crystal called Y2SiO5, YSO. But what we're trying to look at on top of this is calcium tungstate at the very top line over there. And it's got favorable metrics across the 3 that we're looking at, and it's got a good balance. And in particular, we're looking at erbium-3+ as a dopant to this host crystals. So why erbium doped calcium tungstate? We can take this in 2 parts. The first is dopant erbium. So the transitions, the atomic transitions of erbium are in C-band. And this is highly favorable for anything quantum tech where you want to engineer a platform. And it's because existing optical telecommunication networks are operating in this C-band. It's the 1550 nanometer wavelength range. And for the host crystal, we've chosen calcium tungstate host 4 because it's got a low spin off. So the atoms and ions have low spins in the crystal, and this leads to less decoherence when you put in light. And so now I'd like to talk about a recent study that we've just finished and now is on the archive, and it's a simple polarization temperature study on the crystal that we have. And so here we looked at sweeping different polarizations, horizontal to vertical, as well as a temperature between 30 to 30 Kelvin. And in this particular study, we looked at the Z1 to Y1 and Y2 transitions, and these occur for 2 reasons. One, these are the strongest transitions, and second, it is really close to the 1550 nanometer wavelength. And so here, our crystal, the erbium doped calcium tungstate, is actually a tetragonal structure where 2 of the axes are the same and 1 is not. And this gives us 2 different bases, one being symmetric and one being asymmetric. And so, as expected, when we did the temperature sweeps, spectral broadening occurs. So these transitions disappear at higher temperatures, and this is because, when you give more heat, more energy to these atoms and ions, they vibrate more. And this causes decoherence, and these transitions disappear because of it. But a more interesting result here is that the central wavelength shifts as the temperature increases. So you can see on these graphs, the higher temperature you go, the central wavelength shifts to the right. Now, I think this is an important consideration when you're trying to make a platform out of this, and that any fluctuations in temperature causes the operating wavelength to shift, and this needs to be adapted to. The more interesting result was when we looked at polarization. And so here, when varying polarization between horizontal and vertical, we looked at the absorption, central wavelength, and alignment of the transitions. And so the central It's because of these things called selection rules that have been actually talked about in the previous paper already, where we validated the results. And it's really just about the relative configuration and orientation of the incoming electromagnetic wave, separating the electric and magnetic part, and how that's propagating with respect to the crystal. And so if more of these configurations are satisfied, you get a higher absorption. And so another study that we're performing is in phonon engineering. So it's one good thing to cool down to cryogenic temperatures. This gets rid of a lot of different types of vibrations, but even at 20 millikelvin, you will still get lattice vibrations. You're not at absolute zero when you're freezing everything out. And these lattice vibrations, called phonons, still exist. And because they're vibrating, they will interact with light and cause decoherence. And so here is how phonons exist in different energies in the crystal. I believe this is in YSO, Y to the side 5 post crystal, in reciprocal space. So these are bad things. We don't want this, and we'd eventually want to get them out. And so for the host crystal that we're looking at, calcium tungstate, we perform the same. And so we looked at the crystal structure, we validated that the crystal we had through X-ray diffraction was exactly kind of the same as the calculations that we had for it in reciprocal space. And so we were able to map out the different atoms and ions as predicted. And so we went to different places around the world, mainly in ANSTO, Australia, and PSI in Switzerland, to do neutron scattering experiments to detect these phonons. And so here on the right you see results. On the red, those are calculated theoretical energy modes of these phonons, and experimentally we had it in blue, and from Australia and Switzerland. And so in a way they exist in the same energy regimes. We were able to identify the low energy of these phonons and the high energy phonons, and the band gap. There is around 20 millielectron volts between the low and high energy phonon bands. And so the more interesting study that's kind of still going right now is actually measuring the storage time. So when it comes to quantum memories, and especially read crystals, where Van crystals, there's two types of metrics when it comes to storage. The first is the decay rate, known as T1, which is kind of the maximum limit that you can have a storage. And the second is T2, the coherence time, which is the more important one. So you want a coherence in your incoming and retrieve quantum state. And so this is our simple setup in the quantum memory lab, and we're measuring T1 as side fluorescence and T2 as a transmission bar. And so we actually measured this T1, the maximum it can be, and we saw that there's, again, polarization independence, and it was validated by the on-resonance and off-resonance measurements. So, it only happens on resonance around 1532 and 1530. And so still doing storage time characterizations, we're setting up optimization, but more into the future, we're looking at optimizing the crystal environments and our setup. A really cool thing is what they call ZFOS, where you look into the magnetic field and find the right strength of the field to significantly increase coherence times. And of course, with the phonon engineering stuff, we were able to identify the different phonons. Now with these two come together. We're also going to look into spectral hole burning to set up atomic frequency sequence to get better performances of the reed crystals that we're studying. And it wouldn't be a quantum memory if we don't actually do a storage and retrieve of quantum states. So we're looking into that, implementing different protocols. And of course, we don't just want to stay in the optical regime, we're looking at microwave as well. And for diversity, different crystals, not just fermium, calcium, and state. And so with that, I'd like to end. This is the team we have at QLink. It's spearheaded by my supervisors, Young and January. And this is our wider team in the quantum memory lab in QLink. Thank you.
Thank you so much, Mr. Sayat. Any questions from the audience? Anyone? We have one question. We have Mr. Elias Huber.
Thank you for the talk. First, a very basic question, sorry if I missed it. The degree of freedom of the incoming light that you store, is it polarization or something else? And then follow up on that, the previous speaker talked a lot about qubits. And I'm curious if there are any approaches for quantum memories to convert qubits, or like to store qubits and emit qubits. Thank you.
Okay, thank you for the question. So the first part, yes, for the study it was just polarization that we're looking into, and its dependence, and the crystal's behavior on it. So that was horizontal and vertical, and we just continuously turn around a wave plate. In terms of qubits, we actually haven't looked specifically into it. But now that you mention it, it could be something that I raise to the supervisors when I go into work after this talk.
Thank you so much. I believe you can accommodate one more question. We have one. Okay.
Good morning, Mike here from PLDT. I'm just curious as to application with your study. With the recent materials that you've been using, do you see it replacing fiber optics at a couple of years to increase the capacity of communication that we are able to do around the world?
Thank you for the question. So this actually ties well into my PhD, and I'm not going to try to be biased about it. So my PhD was in free space, CDPKD. So I'd like to say that if we were to build some version of a global quantum network, there's two things that I would suggest that would make it better. One is to be hybridized in a way that we both accommodate fiber and both free space. As we know, losses in fiber is crazy compared to free space, and that's why we're doing satellite comms and QKD as a platform to validate this. And the second is actually, in quantum, there's two kind of families that's there for in terms of encoding information, one being continuous and discrete variables. Discrete variables discrete variables are more obviously developed compared to continuous variables, but having both of them with their advantages and that being deployed in certain situations, I think it'd be this very hybrid quantum network would make it very robust.
Thank you so much, Mr. Sayat. Again, let's give Mr. Sayat a round of applause. That ends our Q&A for Mr. Sayat's presentation. So I believe we can start off with the next speaker.
So for our next speaker for this morning is an assistant professor at Chongyan Christian University and lead Quantum Information Center with research focused on quantum computing, quantum machine learning, and quantum algorithms for finance. Ladies and gentlemen, Dr. Yen Ju Chang.
Hi, good morning, everyone, and thanks for the organizer. And today I will show some my previous research and some application of quantum computing in finance. And first, let's see some focus. And you can see the left one is left one is from the McKinsey, and in 2019, you can see the top list. Sorry, I think the solution is not well. The top list of the layer focus. The finance is the potential application, and the right side is from BCG in 2021. You can see that there are four scenarios four occasions in finance. A recent report also from McKinsey, 2024. They show the financial industry have a very important, a very huge market size in about 2035. So we can use the quantum computer to solve financial problem. Maybe it's very have very promising application. So we try to find the best way and find the best method to find the solution on financial problem. So first one we set up a third layer quantum stack. First is we want to find the potential application, and there are four scenarios. And if we want to find a way to use quantum computer, so we need to encode this problem into quantum language and model as some kind of quantum model. So we use the quantum simulation, quantum machine learning, and quantum optimization to represent this application. And then we need to put this model into some device. So there are four kinds of device we can use. The first one is the quantum annealer. We put this problem on the D-Wave. And second one is the gate-based quantum computing. And we use the IBM and Quantanium. And the third one is the simulated annealer. This is a classical machine, but they use the quantum inspired algorithm. So they can specifically solve the some optimization problem with easy model or Kubo formulation. And next one is we use the GPU to simulate the quantum computer. So this is our topic. The first one is the financial modeling. So the first question, why the financial market is super uncertain? Because there are many investors involved in the market. And these investors have different view. Imagine you are watching maybe Apple Apple CEO announce their new product, or maybe you are watching the GTC, and the Jason Huang is announcing their product. Every investor have different vision, so they may feel great about their product or may disappointed about their product. So if you want to make more profit, you may think so. If you feel good, I tend to buy more, and then this way may push the price up. You may feel disappointed. You may want to sell their stock, so the price will go down. Based on this investor sentiment, so we want to design a quantum model that can simulate various investor sentiment to simulate the short-term price distribution. So we want to create an evolution operator that can simulate this kind of behavior. So then we can use this evolution operator to evolve the quantum state to the specific quantum state that encode the probability distribution of the financial market. So let's talk about what is the quantum walk. This is the concept we use to simulate the financial market, to simulate the investor sentiment. So left one is the classical one, and this one has a coin. This is classical coin, and his movement is decided by the result of the coin. If the coin shows 1, he go to the left. If the coin shows 1, so it shows 1, it goes left, and 0 goes right. Sorry, different. Sorry, 1 goes right and 0 goes left. And probability of 1 is p, and the probability is 0 is 1 minus p. So he can toss the coin, maybe he shows 0 and go to the left, 1, right, and he can keep tossing. Sorry. One and sorry. And keep tossing, then he keep walking. And after 6 tossing, he is at the final position. So we can do a lot of experiment and get the final probability distribution. Then you can see that if there's there are quantum coin, and this coin can control the coin probability, but in the quantum physics, we only use the quantum state. So the quantum state, if the state is 0, and its amplitude, its probability amplitude is cosine theta over 2, and if the state is 1, the amplitude is the EI phi sine theta over 2, and so in this case, these people, this worker go to right when the state is 1, so the probability of the state is the square of EI phi sine theta over 2. And he goes to the left, is the cosine theta over 2. So we use this quantum coin to simulate the distribution. If you use the quantum coin, you can simulate all paths at the same time. So because we have the different phase, EI5, so we can provide more flexibility to simulate complex distribution. And we can do the final measurement. It can show, you can say that he is at the final state. Because we have more parameter, so we have ability to simulate different or complex distribution. So this is our this is our concept to simulate the market distribution. So we use the variants of the quantum world. We call that the speed state quantum world. You can see that this quantum world, we can use the quantum circuit to simulate this kind of algorithm. And you can see the left side. W is the worker's operator. We divide the operator to several parts. The first one is CCTR1. It controls the worker to the right or stay at the same position. And the second, CCTR2, it controls the worker if he stay. You can see that the second coin, if the S minus operator shift S minus, it controls the worker to the left if the coin stays down, and if the coin stays up, he remain his position. You can use the right side of quantum circuit to simulate this distribution. So P1, P0, P1, P2, P3 is the position Hilbert space. C is the coin Hilbert space. So we use a universal gate to change the coin state. If you can see that if the coin is 0, the discriminator will apply. So he may push the worker to the right. This can represent like the investor. If he feels sad, he may sell the price. He may sell the stock and push the price down. And the second one, we can simulate investor sentiment again and show the quantum state. You can see that the second conditional shift operator is a solid dot. So if the quantum state is 1, he will increment the position. They will push the worker to the right. It can represent that like an investor, he feel great. He want to buy more stock. So push the price up. So we use a VQC, parameterized quantum circuit, to simulate this kind of distribution. You can see on the right side, the first red block represent the investor 1. And this red block represent the first investor settlement. And the second and third, and each red block can represent each investor settlement. So we can see that there are many investors in the market, and their idea is like are like the superposition. So we can use the quantum circuit to simulate their idea, and we can get a result, and we measure the position and get a result. We use the cluster optimization to tune each coin. So the right side is our result. this is real market distribution. We can say we use the Google, Nasdaq, Apple, and S&P 500 real price distribution. We use this circuit can exactly simulate this distribution. And this is our paper, and you can, if you are interested, you can see that paper. It published in Quantum Machine Intelligence. And the second one is fraud detection. In this application, we use different methods. We use the Kubo formation. We use annealing algorithm to find the best solution. So let's talk about annealing. Annealing is like annealing use the easy model. An easy model is a model to simulate the magnetic system, and their energy can write in H, and the first term is the interaction energy, and the right term is side energy. So annealing is there are two kinds of algorithms to find the best configuration of this energy. And first one is the quantum annealing. The second one is simulated annealing. There are two different methods. Quantum annealing uses the quantum tuning. So they use the real hardware like D-Wave to get the solution. Simulated annealing, they use software algorithm. So it can run on everyone's laptop. You can run on everyone's laptop, so we can use this algorithm easily. So if we want to use annealing algorithm, so we need to encode our problem like this easy model form. So let's talk about annealing feature selection. This is our second application. So we use blockchain data to implement our algorithm. So we download the data and pre-process on blockchain. And as a matrix, so each column represents a feature, and each row represents space data or a particular address. And we also get the result of the address. So if we want to know which address is miser is a bad address. It always connects to money laundering. So we want to find this bad address. So we use the data we download, and then we can use the supervised machine learning to identify this bad address. But there are too many features. So we want to reduce this feature, and we can use less time. You can use less computing, less time to identify this address. So we did the annealing feature selection layer into the before the supervised machine learning. So the annealing feature selection we write as this function. The first term represents the inference of the feature, and the second term represents the independence of the feature. These two can be write as this form. In this formulation, the variable xi only shows 0 and 1. It's a binary representation. And rho vj is the correlation between the feature and the address. And the second term, rho jk represents the independence. And we use the correlation between two features. So we use this algorithm. We use this feature selection. Sorry. Into real data. You can see that the 7 top is top of 7 is the supervised machine learning without any selection. And I think there are 78 features. And you can see that there is a baseline random forest. They shows the best result. And they shows the F1 equal to 0.92 and AUC is almost 0.99. And if we put the formulation into simulated annealer, we get 23 features. In this 23 feature, random forest also gets the best result. You can see that the performance reduce very small, but they have huge decrease in time, about 30%, from 300 minutes to about 200 minutes. And we also put this algorithm into Kubo in the quantum annealing. They tell us 9 and 7 result, but they show the worst performance. On left side, you can see that their time. Classical simulation only use about 5 milliseconds, and quantum annealing use about 6 seconds. And this also published a quantum machine intelligence. And the third one, I think, almost run out of time. So we also used to this is our third application about portfolio optimization. About portfolio optimization, we always use the modern portfolio theory. This is famous theory. It can maximize the return and try to reduce the risk. And they can get the efficiency frontier. We want to get the portfolio on the efficiency frontier. It's most efficient. If be upper the efficient frontier, it is impossible. If you below the efficient frontier, so it's not the best. You can find the best of portfolio. You can see if you at the red dot. So you can find the better portfolio with the same risk level, but you can have more return. So we use this formulation to find the efficiency frontier. So because if we use the Kubo, we need to use binary representation. So we encode our weight into binary representation and put into the Kubo formulation. So the second term is the return target penalty. We want to fix some return and find the best, minimize the risk. So the second term is our objective. So we use the Kubo formulation to simulate the distribution. The radar is our we apply our parameter theory algorithm. So they can show the better solution. You can see that radar is very close to the efficiency frontier. And okay. So maybe I can just jump faster. And the other one. And we also use on the currency arbitrage. So we encode the objective and constraint to the Kubo formulation. And the first term is we want to maximize the profits. And the second term is constraint. It includes we want to make a cross loop. And we also calculate the cost. So the middle is our data we input. And the second one is the loop we find. And the third one is, you can see that third one, the profit is larger than 1. So we can use this formulation to find the best loop to profit. Oh, this is the other. So we also use this kind of formulation to do the material finding. We cooperate with the Formosa Plastic. They want to find a material that encode a phono, and we want to put more addictive into this material. And we cooperate with their expert and learning their domain knowledge and encode this problem into CUBO formulation as a script. And we can screen then about 50. Once we can screen some material, and they show that if they use brute force, they need to simulate 500 times and use about 7,000 hours. And if they use the machine learning, they screen out about 1,000 material and use 1,500 hours. And they use a nearly. They provide about 500 material. They only use 7 hours to get the result. So this is our last application. And the next one is, and this is our activity in Taiwan. And we call a quantum forum in Taiwan in September. We also invite some best solution. Maybe IBM, Redacty, and D-Wave, and Google, and Quantaneous, and some startup company, IonQ. They will show and give us their view in Taiwan. So it's my talk. Thank you.
Thank you so much, Mr. Chang. Any questions from the audience? Yes, we have one question right here.
Good morning, sir. Thank you for the very good presentation. I just would like to ask, because you are using quantum computing to model financial management. Now, I'd like to ask if you have data on the success rate of your model when it comes to the prediction of short-term prices of the portfolio or the stocks that you are in. And secondly, with this kind of model, is it safe to say that, setting aside the risk appetite of the investor, is it safe to say that we can make more gains in timing the market, because we have now the model? We can go into timing the market now, rather than in long-term investment.
Yes,
which is more profitable, do you think? Because we wanted to make all money in the stock market, I think. Thank you, sir.
This is our first step. We just want to find out our algorithm can simulate the probability distribution. In this model, if we can tune the parameter in a coin, then we can control the probability. So if we can produce or learn some data from the real market to produce this parameter, and then we can try to, maybe we can produce, we can create the future probability distribution. Yeah.
Thank you for your presentation. It quite opens the avenue to use quantum computing in financial. So it's more like an application from the things that we have learned from the last 2 days. So as what I have seen in your presentation, some of the simulation, you actually compared the performance of quantum computing against the classical. And in some classical, the classical, meaning the von Neumann, the 0 and 1s, you compared your performance of your algorithm in quantum computing against the classical. So it's part of your slides, and it seems that the classical computing architecture is still better performing with the quantums one. And then my question is really more on like, how can we, this is the first one, how can we convince the the granting research grant agencies that we're going to use quantum in this particular kind of application when they already like see some of the literature that classical computer is better than quantum. So isn't it an overuse of resources to really go into quantum than using classical computing for the same task? That's the first one. Second is, what is the number of qubits that you use in your simulation? Because it is not discussed in the presentation. Maybe it's because of the time.
I think we use different device because we use different encoding method. And if you can see that if the first one, we want to try to simulate the distribution, zero goes to right, zero goes left, and one goes to right. They have different distribution. So we use the quantum circuit to simulate. We encode this problem into superposition state. Yeah. So we only can use the gate-based quantum computing. But if the problem we encode into the 0 and 1, so we can formulate this problem into Kubo formulation. So then we need to put this formulation into the quantum inspired, we call it quantum inspired machine. They can find the best configuration with lowest energy. So I don't know which device is great, but the problem is the key is what encode method to discrete our problem. So we choose then we choose different machine. And the second one, sorry.
The second one is the configuration of how many qubits did you use in your simulations?
So in the quantum world, we only use the maybe 5 or 6 simulate qubits. So we can run on classical computer. We use the simulator because in the quantum circuit, in the quantum world, I don't show the detail. Yeah. In incriminator and discriminator, there are many multi-control gate. They are very expensive and brings much more noise. So we don't run it on the real quantum hardware. And if we use the Kubo, I think we use about almost, I think 1,000 of variable. But it is affordable if we use the annealing machine or quantum inspired machine. Okay.
All right. If I may have just one more question. So we use 6 qubits for the simulation, and in the 0-1 simulation there is a distribution.
Yeah.
So from the result of the classical and the quantum computing simulation, which do you think has better configuration results? Is it from the classical or the quantum result? Because the performance is faster for the classical,
yeah,
and slower for the quantum.
Yeah.
But when it comes to the result, do we have a better distribution from classical or from the quantum?
I think that if we use the simulation, I think it can provide the exact solution.
Exact solution.
Yeah, you can see it's just a linear algebra operation. You just do the matrix dot vector. You can get the final vector, so you can change the final vector into the probability distribution.
Okay, thank you very much for that one.
Thank you so much, Dr. Chang. Let's give Dr. Chang a round of applause. and we may now move forward.
Okay, thank you so much, Mr. Lance Raquel and Mr. Jang, for the insightful discussion. Now it is time to hear from our very own researchers in the Philippines. This session will discuss ongoing quantum research from the government and academic institutions. Let's welcome on stage our moderator to this session, Mr. Dylan Josh Lopez.
All right, hi. Hello, so my name is Dylan, so I'm the Director for Collaboration and Partnership, so it's my pleasure to introduce these projects from the Philippines. So first up is our science research specialist from DOST ASTI, Mr. Ross Romuel Mariano. Ross Romuel Mariano is a science research specialist at DOST ASTI. He serves as a technical lead in the Quantum Innovation Laboratory, where he drives education, research, and development in quantum computing and software. Ross specializes in quantum software programming using QISTCon and trains researchers in quantum circuit simulation and advancing computational methods. He also leads initiatives in quantum image processing, exploring how quantum algorithms can transform fields like medical imaging and remote sensing. He's also active in outreach. Ross regularly represents at national conferences and conducts trainings to build a quantum-ready workforce in the Philippines. Through his technical leadership and advocacy, Ross is playing a vital role in advancing quantum technology, research, and education, helping position the Philippines as an emerging participant in global quantum information landscape. Everyone, let's welcome Ross.
Hello. Okay, so good morning to everyone. I am Ross Mariano from DOST Advanced Science and Technology Institute. So today I would like to discuss initiatives from our very small group from the Quantum Innovation Laboratory. So before I proceed with my group, I would like to introduce my institute, the Advanced Science and Technology Institute. So DOST has many institutes and agency under it, So most of us are familiar with Pag-asa and PIVOX, which are the technical services agency of DOST, and there are other agencies also like PSURE, which are governing councils, and there is a group of agencies which we call the Research and Development Institutes, and one of those is my office, ASTI. So what does ASTI do? So the mandate of ASTI is to drive research and innovation for the country. So most of the what we call emerging technologies, the technologies that are new to the country are being assigned to ASTI. So I remember the other day there was a guy who worked for ASTI before. He said he was working on Bluetooth technologies. And if you know PhilSA, Philippine Space Agency, before PhilSA was formed, a lot of the space technologies were being developed in ASTI. And in recent years, the emerging technologies that we are tackling are artificial intelligence, blockchain technologies, and our topic for today, quantum technologies. Okay. So under ASTI, we have a very small group. We call ourselves the Quantum Innovation Laboratory. So right now we are only composed of 3 members. So that's me and 2 of my colleagues. So we have backgrounds in physics and computer science. And what we are trying to do is to focus on the computational side of things, which is, I think, quite different from a lot of the speakers that presented, which focused on hardware and photonics. So we are trying to study computing paradigms to focus on quantum algorithms. We are studying quantum-driven problem solving. How can we use the well-known quantum algorithms, your Shors, your Grovers, on applications to different problems in the country? And how can we test this for simulations, particularly on our HPC, the core HPC. So our projects include this, the Quantum Circuit Simulation Project, or the QCS project, which is one of the first, if not the first, DOST quantum computing related project. No? So using the core HPC of ASTI, we aim to develop and benchmark quantum algorithms via classical simulations, and how can we use this, our HPC, to help researchers and academics from different fields. So through the QCS projects, we have published and presented a few papers on it. No? So first is benchmarking decision diagram models. No? So we are, aside from the quantum circuit model, we are also looking at other computational models, no? Namely the decision diagrams model and the tensor network computational model. Then we also published a paper on Philippine education, or how are we contributing through the quantum education in our nation. And one paper on this quantum walks on full binary trees. This is more of a physics paper that we presented on SPP. Then another much smaller project, no? So this is more of a exploratory project, which is quantum image processing. So why did we choose image processing as an application compared to every other possible application? No? So since we see quantum computing as an extension of classical computing, no? How we were thinking, what is ASTI doing right now that we can apply quantum on? No? So a lot of the projects in ASTI right now, they include image processing, they include computer vision, satellite imaging. So that's why we chose image processing as our project. No? So we are looking at how can we encode image data into quantum data, then how can we use that quantum data for our quantum algorithms. So this is an ongoing project right now. And so for now, we only have those two projects, no? But we are planning to hold more projects in the future as our team grows. No? So aside from the quantum circuit simulation project and the quantum image processing project, we also offer internships to undergraduate students. No? So for this year, we have 5 undergraduate students from different universities from the Philippines, and we are very fortunate that they are interested in quantum information and quantum technologies. And so our interns are tackling projects in quantum image processing, quantum software engineering, and quantum security. Then we also regularly hold educational activities. No? So a lot of them is together with the organizers, no? Quantum Computing Society of the Philippines. No? We hold lecture series, we hold hackathons, and we also regularly meet with faculty from other universities for them to be involved in the quantum scene. And so a few of this is also from conferences that we attended. Yeah, so it's only a very short presentation. No? So what we foresee as a representative from the government, we would like to strengthen collaboration between the academe, government, and industry. And we strongly believe that we need to include quantum computing and quantum technologies into our academic curriculum. And we also need to develop long-term projects to sustain the quantum workforce. And hopefully in the future, the Philippines is a major component in the quantum scene. Okay, so that's all for my short presentation. Thank you very much.
All right. Thank you, Ross. So I know some of you have questions for Ross, but we'll reserve that for later. We're going to format this a bit of a fireside discussion. So we'll finish all of our presenters today, and we can have all of their questions in one go. All right. So we're now up to our next speaker. So our next speaker is Dr. Maria Teresa G. De Leon. She is a professor at the University of the Philippines Electrical and Electronics Engineering Institute, where she plays as a leading role in microelectronics research and education. As a deputy director for academic programs and a member of the Microelectronics and Microprocessors Laboratory, she advances the fields of analog and RF integrated circuit design, MEMS, and microfabrication. She earned her PhD in electronic and electrical engineering from the University of Southampton in the UK and holds both MS and BS degrees from UP Diliman. Dr. De Leon is active in projects on MEMS-based sensors, RF circuits, and energy-efficient hardware, regularly publishing in international conferences and journals. A committed mentor, she could guide students on semiconductor devices, circuits, and system-on-chip design while promoting diversity in engineering. Through her research, leadership, and dedication to teaching, Dr. De Leon is instrumental in preparing the next generation of Filipino engineers and strengthening the microelectronics community in the Philippines. Everybody, Dr. De Leon.
Thanks, Dylan. It's a very warm introduction. I hope I can live up to that introduction. Anyway, so I'm Maria Teresa De Leon. So let me see, check it. You can call me Tess. I'm a professor at the Electrical and Electronics Engineering Institute of the University of the Philippines. As Dylan mentioned, so I'm fairly new to quantum. Probably before this conference, I've heard about quantum a lot during an physics course while I was an undergrad. So that was a very long time ago. But I really learned a lot in the past 3 days. So I'm very thankful for the invitation. So as you can see, the title of my talk is actually something that's going towards the fabrication of photonic integrated circuits at UP Diliman. So what I'm going to present today are the work that I've done, specifically related to device fabrication, that sort of gave us a bit of confidence that maybe photonics is something that we can also do here in the Philippines. So a little bit about the facility that we have in UP Diliman. So this is housed not in my institute, but in the Department of Mining, Metallurgical, and Materials Engineering, but it's very close to our institute. Back in 2018, I was lucky to get a grant from the Commission on Higher Education, where we were able to establish a clean room facility in UP. So the main motivation for me there is because I was able to work in a clean room while I was doing my PhD, and I thought a lot of insights that I learned, I want my students to also undergo. So back then, so we established 2 rooms. So one is the white room, or the clean room, where we house most of the characterization, equipment, plasma, deposition systems. And on your right is the yellow room, where we do most of the wet processes and the lithography. So this was actually funded by a project which we call VERSE, so Vibrational Energy Harvester for Resilient Sensor Nodes, which started in 2018. And as part of this project, this was a PICARI project. So it's a Philippine California Research Institute grant, wherein we partnered with UC Berkeley. So most of the researchers actually went to UC Berkeley to train in their facility there before, while we were establishing the clean room. So we had to build the clean room from scratch. So sorry about that. So the main idea about the project is that we wanted to harness vibration in the environment and create this device, the piezoelectric cantilever there, wherein due to those vibrations, we'd be able to harness electrical energy. And these are the researchers. So I'm just an academic, so mostly doing mentoring, but the ones who do the grunt work are really the grad students and the researchers. And we looked at several materials. So while they were in Berkeley, they worked with PZT, so lead zirconium titanate. But because of the lead component there, it's a bit toxic. So we also explored other materials that, although less efficient, are more environment friendly. So just to show you a video of some of the work that came out of these projects. So we were able to fabricate these multiple cantilever structures, and we had a shaker system, so we shake it at a certain frequency, and as you can see here, when the shaker is off, there's no output voltage, and then when the shaker is on, we measure the voltage from the electrodes of the cantilever. And along with this, because of my integrated circuit and chip design background, I also had a team who worked on the power management unit. So from that AC signal, they had to convert it to DC so that it becomes usable. But I did not include the slide of the IC here because I know this is more on a quantum, and so I want to highlight the fabrication aspect of my research. So after that project, I was also part of a team from my lab that proposed another project. This time was funded by DOST under DOST PSHIRT, which is the Center for Integrated Circuits and Devices Research. So this program is composed of 4 component projects. The 3 component projects focus mostly on chip design, while my project, Project 2, tries to bridge the physical world through the sensors, the local fabrication of the sensors, with the interface electronics. So in this project, we did co-design of both. So we did the design of the sensors locally, and then the interface circuits we designed using the technology that we use to tape out our chips. So for the sensors, we explored 3 types. So a thermopile temperature sensor. So the ones that you see here on the screen on the left are actually fabricated already in UP, and they are already tested. And then we also have another team, the chip design team, who did the interface so that any change in temperature that's measured from the sensor can be translated into an electrical signal. So we also did surface acoustic wave sensor. So this is already ready for testing, this device shown here. And then we have the interface circuit related to that. And then we also did piezoelectric pressure sensors. So a lot of the work that we did on fabrication, aside from doing the device itself, is really more on studying the material. How do we come up with better material so that we get to have better sensitivity for our sensors? And so therefore relax the specifications of the chip so that we don't need to use a lot of energy to be able to convert the physical signal, let's say temperature or pressure, into digital or ones and zeros. Yeah, so here's just a short video of the SAW sensor that we did. So you can see here we have attached it to. So the idea behind the SAW sensor is that if there's a change in temperature, you will see a shift in the resonant frequency of the device. So you'll see here that you have a heat gun pointing at the device, and then when you turn on the heat gun, okay, the network analyzer with the signal there, you'll see that the frequency will shift as the temperature goes higher. So therefore now, the electronic circuit that interfaces into that sensor would have to translate that shift in frequency into a signal that can now be converted into digital, because we usually do the compute using digital circuits. So you'll see there, again, these are the researchers. I really have to include them here because they did the work. Yeah, so, and another thing, so that's, the previous one is going to end this year. So we're finishing up with completing the sensors that we're fabricating, and then of course going to do a terminal report on that. But last year, we had a meeting, it's not really intentional, but we went to a meeting where we had doctors from UP Manila, and they were presenting their work on tuberculosis diagnosis. And their focus really is on the biological assays that would allow them to use less volume of sputum to be able to detect TB. The problem that they're trying to solve is that they want to have portable diagnostic devices because TB is prevalent in the Philippines and they want to reach the far islands to do the diagnosis there. And when they got to talk to us, we said that normally what we see in literature is that there are these microfluidic devices that are used and they can work with small amount of reagents, but of course they have to do the biological side. While they actually allotted one researcher for us. They said, okay, we'll give you funding for one researcher. Let's try to explore this part of the field. So yeah, so these are some of the work that we've done here. So it's fairly new for us. So we've already done some modeling of fluid flow in a, let's say, microfluidics capillary pump. And I'm not sure if it works. There should be a bit, yeah. So you can see here we've also done some fabrication, tried to look at how liquids mix in these types of capillary pumps. So these are all capillary driven. So there's no external stimuli that mixes them together. You just put them in an inlet and then this is how it goes. So it's still new for us, so we're still continuing with this work. Yeah, so now that brings us to what we plan to do. So late last year, we proposed another project because we were approached by ASTI, and they said that they also, maybe we would like to look into the device part of quantum. So we read a bit and then, okay, maybe it's something that we can explore. And luckily, we got funding. So this is still about to start. So I said 2025 to 2027 there, but we still haven't started yet. But what we plan to do really is to first study what structures, what photonic structures can we fabricate given the equipment that we have in our facility. So these are the slides that I used during the defense of the proposal of the project. So you can see a complete computing chip on the left and some of the components of a quantum computing chip to the right. So we're looking at really starting with waveguides, setting up the test system. And of course, if we can try to simulate this because it's easier to be able to understand first how these structures work before we start fabricating them. Yeah, so these are the objectives of the project. I don't want to bore you with them, but really, it's really eye-opening for us to attend, for me personally, to attend this conference because now I have a better understanding of how these devices will place in the quantum stack that Mr. Manalotta presented, I think, yesterday. So we'll do some multiphysics simulations, we'll perform some fabrication, and we'll set up a test system to be able to characterize these structures. And hopefully, by the end of 2 years, so this is just a 2-year project because it's mostly exploratory, we'll be able to come up with maybe a Hadamard gate or a NOT gate. No? And that will be a win for us already. Okay, so what's next for the facility? Of course, we'll still continue with what we have done. We are looking at mixing some of the things that we did. So for example, can we use the SAW sensor to actuate some of the microfluidics processes? Can we use some of the temperature sensors to sense if the liquid is already heated at a certain temperature? So that's what we're looking at right now. But of course, because of the funding that we got, we're also heavily invested into looking into silicon photonics for not just quantum computing, but also for communications and sensing. Yeah, I think that's it. Thank you for listening.
All right. Thank you, Doc Tess. Now, for our next presenter, he is also in the field of PICs. So let me introduce to you Dr. Benjamin Dingel. He is a distinguished Filipino-American physicist and a photonics expert with over 3 decades of experience spanning academia, industry, and innovation in optical science and engineering. He earns his bachelor's in physics in Ateneo de Manila University and has his master's and PhD in applied physics, specializing in optics and photonics at Osaka University in Japan. Dr. Dingel has held research and leadership positions in top international institutions, including NEC Corporation and CRL, Ministry of Post and Telecommunications in Japan. Also, he has also been a senior researcher scientist at Corning Incorporated in New York, where he is involved in integrating photonic circuit technologies and broadband access systems. He co-founded also NASFINE Photonics Incorporated, serving as the CEO and R&D director to develop advanced photonic integrated circuit technologies. He also currently serves as the head of Ateneo Research on Optical Sciences and Engineering and Systems, or ROSES, and he is a research fellow under the Ateneo Research Institute of Science and Engineering, or ARISE. At Ateneo, Dr. Dingel leads on hands-on publication-driven research programs in photonics, training the next generation of Filipino scientists and engineers. With over hundreds of peer-reviewed publications and more than 10 patents in optical system design, Dr. Dingel is recognized internationally for his pioneering work in optical and microwave photonics, PICs, optical signal processing, and sensing. He is a former senior editor for SPIE and has chaired numerous international conferences in optics and photonics. Through his leadership, Dr. Dingel has bridged global R&D expertise with Philippine innovation, advancing photonics research, education, and technology development in the region. Everyone, Dr. Dingel.
Okay, thank you very much. I'm asked to stand here and rather there, so I don't know why. But, where's the first? Okay. Now I have it. Okay. So again, my name is Benjamin Dingel from Ateneo de Manila, Department of Physics and Ateneo ROSES Laboratory. So the title of my presentation, and I'll try to make it 10 minutes as much as possible, is The Path Toward Quantum Computing and Communication Capabilities in Philippines, with the subtitle of It's Pivot-Aware and Pivot-Driven Approach on Research. During the first day of the conference, there was a question how the Filipinos quantum computing should be or characterized. We have around community-based quantum computing and many different types of computing around the world. And to us, the ROSES Laboratory, we are driven by the idea that quantum in its nature keep on changing, not only in the implementation side or in the overall setup of the ecosystem, and so we cannot predict what it will come out. And so our research in Philippines should be pivot-driven. Anytime that will come out, it should be able to pivot anytime. And maybe I will talk more about this in the later part of the talk. So let me introduce Ateneo ROSES Laboratory. We started around 2018, and we have four faculty members and around 8 RAs coming from physics, mathematician, computer engineering, and electronics engineering. I would love to have a psychologist, behavioral psychologist in the group, but I still have not been able to do it. I do believe that psychology is very important, especially in quantum communication. So we are one of the active members in active laboratory in the physics department, and we have received roughly around 50 million to 55 million of grants from the DOST, the University Research Council, to pursue what we are doing. Okay, so humble claims on the photonic integrated circuit in ROSES Laboratory. We are, if you look at the poster outside, the poster there on number 5, I think, in the PIC, our work there is demonstrated or reflected. We are the first Filipino group or research lab that have designed a Filipino local design PIC. That's one of our claim. And then our second claim is that in all PIC design that we have, we always introduce a novel optical element that will make us a little bit different from the existing or competition abroad. And so it's still minor, but it is a very different that makes us a little bit different from our competition abroad. Number 3 claims is that we are the only laboratory right now who have a testing and characterization facilities on PIC. I know Doc Test, they're coming up with another photonic integrated circuit test and characterization laboratory, and I think it's a very fruitful endeavor. We can all learn from the work of other people. And so, okay, so about our, about our grants from the DOST, we have 3 works on photonic integrated circuit base. One is the eAsia Joint Research Program with Japan, Thailand, and of course Philippines. We are supposed to deliver a PIC design on multifunctional filter, and that is useful also for sensing. And number 2 is the Kepler project. This is rather unique to us. It has application in aerospace and aero engineering. We like to mimic, we found out that we can mimic the position of satellite through photonic integrated circuit. And number 3 is we are also working on 5G application, but on a specialized field, which is a subunit in 5G, which we call linear optical frequency discriminator. Now, what does it mean? We believe that photonic integrated circuit is enabling technology for a lot of application. And one of those applications is quantum computing and quantum communication. And we are not the only one who have this idea. A lot of the international community have this perspective. Now, just to bring up I will not go into the details, but quantum computing based on photonic IC has many advantages, many advantages and disadvantages on the different format or modalities of quantum computing. We believe that quantum computing is one of the attractive platform for quantum computing in Philippines. Now, what do we do in quantum computing in Rose's laboratory? We would like to specialize on the novel PIC design on quantum operator. We do not like to operate the whole spectrum or the whole food chain of quantum computing. We like to specialize only in certain areas. And in that areas, we like to cover the quantum operator by introducing new elements in the quantum computing operators. Now, looking forward, if you look at my presentation, the idea is that in order to compete globally and locally, we have to be aware, or we have to have a mindset of a quantum nature. We need to be pivot aware, pivot driven, and hopefully pivot ready in all our decision in the research. What I meant by this, I think quantum computing, photonics computing, and photonic assisted AI are very related. And so we need to select certain aspect of the program or certain aspect of research in order to pivot from one channel to another channel or another field to another field. I'm old enough to experience the bet of the demise of Nortel. It's a big company, but because of a wrong bet of a technology, the company is now disappeared. Also, the Bell Lab, a very famous laboratory in research, it's been absorbed because of a wrong choice of technology during the optical internet. I was part of the optical internet researcher during that time. And also recently we have experiences right now. Intel is having a problem with their role in the, or not in the role, but in the technology. They made a bet on the PIC, not in the PIC. Of course, they did the PIC as well during the 2025 time frame, but now they sold it already. So the bottom line is, we Filipinos, or we in the Asian countries, we have very limited resources, very limited human power. So we need to be very vigilant, and we need to be very choosy in getting to the quantum arena. And my proposition is that from the start, we have to be very aware. We need to pivot very early. We need to be driven in our research that is pivot adaptable, so to speak. Quantum is a very interesting field, but also a very dangerous area to commit. Okay, thank you very much. I forgot to thank, sorry, I forgot to thank. We would like to thank the DOSTP shared for all the support we gained, and also for the Quantum Computing Society of the Philippines for inviting me. Thank you very much.
Thank you as well, Dr. Dingel. All right. So now we are left with our two presenters. So let me introduce our next presenter. So our next presenter is an accomplished electrical engineer, researcher, and educator with deep expertise in power and energy systems. Dr. Gerard Francesco Apolinario holds a PhD in electrical engineering from Chongyuan Christian University and currently serves as a professor at the Electrical Engineering Department of Technological Institute of the Philippines, Manila. As a dedicated educator and mentor, Dr. Apolinario has guided aspiring engineers while publishing extensively in reputable journals. His contributions have played a significant role in advancing smart grid technologies and promoting sustainable energy solutions. He is also currently the lab coordinator and head of QISLAP, Quantum and Intelligent Systems Laboratory for Power Engineering, the country's first dedicated research laboratory focused on integrating quantum computing into power engineering research and innovation. Everyone, let's welcome Dr. Apolinario.
Okay, good morning everyone. Thank you, Dylan. So, fun fact, Dylan and I have been on the same laboratory. And why did I decide to go on quantum? 3 years ago, my advisor, Professor Hong, told me, Francesco, enroll these courses. Try to integrate that into your dissertation. I was studying unit commitment problems. So unit commitment is a combinatorial problem. Let's say you have 1,000 buses. Each buses has, let's say, 6 binary values. 6 binary values considers 2 states. Then you have a time step period of 24 hours with 5-minute resolution. So try to look at the complexity of the problem, and my advisor just told me to study that. So going in that, I said, wow, I think I would not graduate in 2023. Maybe I would graduate 2030, 2035, I don't know. So instead, we just focus first on understanding what would be the, let's say, perks if we use quantum computing. So instead of diving it into my dissertation, we instead try to integrate it into a grant proposal under DOST. So that's why we come up with this one. Quantum computing-based forecasting and optimization applied to electric power grid. Okay, this started September 2024 and hopefully it would stop by August 2027. So why did we have this code name Kuryente? So what is the meaning of Kuryente? Okay, so Kuryente is just a homophone for Tagalog word or Spanish loan word Kuryente, which means electricity or electric current. If we look at the previous discussion, electricity and qubits have one similar thing, electrons. The flow of electrons produce electricity. Spinning of electrons for quantum mechanics. So that's why we codename it as Kuryente. So what we try to do is to have a test case of applying quantum computing principles for power and energy field. So here is the project members as well as the project staff under this project. So another reason why we've decided to go on here is because of the quantum worldwide effort. So around 2025, we could already see that the whole world is already advancing in the application of quantum computing. Another reason is we are already in the fault-tolerant quantum, we are already in the NIST period or the noisy intermediate scale quantum computing, and we could see here the possible applications such as quantum chemistry, optimization, and machine learning. So going back on what my advisor told me and going back on my previous dissertation, unit commitment, economic dispatch, or anything regarding energy optimization, energy problems goes with either machine learning or optimization. We try to look it in terms of the Philippine aspect, in terms of the Philippine Energy Plan. So in terms of Philippine Energy Plan, Department of Energy always tells that we are trying to have a sustainable and clean energy future. Doing that in case, what do we need to do? We need to plan our renewable energies, we need to optimize our grid, and so on. At the same time, if we could try to prove it in this electrical engineering application, we could go to other types of applications such as logistics, supplies, or control. So our project is divided into two subcategories. First one is to the development of an industrial proof of concept. The next one is to develop supporting activities to further quantum computing in the Philippines. First one, focus more on creating a predictive analytics and a prescriptive analytics. But take note that we would be using hybrid quantum computing. We would not be focusing only on quantum computing. Main reason, we all know the disadvantage, we all know the limitation of the quantum computing aspect. On the other side, we'd focus on developing activities such as conferences, capacity building, socio-economic study, and a position paper wherein are we really ready for quantum computing in the field of energy, or is it too early? So this project would try to show, or hopefully after 3 years, we would see if we are ready for it. Here is the tentative framework of how we would be doing our research. So we have data collection considering electricity price, solar irradiance, wind speed, and electrical demand, wherein we try to forecast it using hybrid quantum forecasting modeling. wherein this data would be integrated to what we call the unit commitment scheduler, wherein it would show how many committed generators, what percentage of renewable energy you have already in the system, and so on. Then, we consider uncertainty. Uncertainty in the electric grid is very much prominent. So if you remember last April, we have the Spain and Portugal blackout. Main reason for that is the sudden drop of the working generators. And this is under real-time scenario in less than 5 minutes. So it would cascade in the whole system. Once we have developed this through prototyping, we'll try to put it into a simulator. So maybe the first part would be the use of CUDA Quantum, then maybe the D-Wave, Rigetti, IonQ, or Kera. So this is the first part of our operational validation. Once we see that it's applicable, we could already go to the next one. So we have validated the operation, but we need another part. That would be industrial validation. So we have partnered with an electric cooperative in the Philippines, which is Batelec One. We also have tried to have talks with Department of Energy for them to validate if ever our resulting research is okay or not. So here's our tentative software architecture. So we have here the local HPC that is developed using conventional software such as Ciplex, Groby, and so on. We'll be also using NVIDIA Quantum as well as Python. We'll try to put it into our third-party cloud quantum services such as those. Afterwards, we proceed into our cloud deployment, which is divided into 2 instances. The first one would be the forecasting cloud compute. The second one is for the unit commitment cloud compute. And this would be put into the client perspective. Another output of the project is what we call KISLAP. So KISLAP in English means sparkle or a sudden surge of energy. So we claim that this would be the first laboratory focusing on applying quantum computing for power engineering problems, but we still focus on hybrid and classical. Main reason for that is the limitations as well as the problem as of now for quantum computing. But as we all know, there should be always test cases, there should be always application. If we just focus more on the principles and we does not go into deep into its possible applications, it would not be something viable. So that's like what we have done yesterday in the quantum diplomacy game. Looking forward in the future, what we expect for the KISLAP would be to have what we call the quantum energy ecosystem. So what does this mean? If we have a quantum energy system, we focus on other technologies trying to integrate it together, such as what we call the smart decision support system or a smart energy management and protection or protective system. But for the project, we'd be focused more on the hybrid quantum decision support system. So what does this quantum energy ecosystem means? Here are the possible applications that we could see. Power producers, energy transport, electricity market, and power system operation. And with that, I would like to thank you for listening.
All right, thank you, Dr. Apolinario, for your presentation. Okay, now we're down to our last researcher for this morning. So I'd like to call on our next speaker. Our speaker, Dr. Mark Angelo Purio, attained his PhD at Kyushu Institute of Technology from Fukuoka, Japan. He is actually a celebrated space engineer here in the Philippines, where he's one of the pioneering engineers in developing microsatellites for the Philippine government. So as a space systems engineer and faculty researcher at Adamson University, leading research at the intersection of quantum technologies, AI, and space-based systems. He heads the project Starkey and contributes to the Philippine Quantum Technology Roadmap through his work with the Minerva Labs in Adamson University, focusing on energy and disaster management solutions. Everybody, let's welcome Dr. Purio.
Yeah, good morning, everyone. Thank you for the kind introduction, Dylan. Actually, this quantum-related research is not really my research initially. It is actually written with Adamson and also TIP with Dr. Apolinario. It's just that things happened in the middle. That's why we were able to get this project. Again, I'm Dr. Mark Angelo Purio. I'm from Adamson University. The project is Project Stark. In the OST, catchy titles are very important. However, we started Stark as space technology, artificial intelligence, and quantum algorithms development for e-vehicle and renewable energy infrastructure planning. However, they told me na since this is a quantum-related project, it should start with quantum. That's why the new title. But I'm here as an imposter. I came here because I'm not a quantum practitioner. My field is really electronics. I'm a product of UP Diliman's CDIR before. Also a product of Stamina for Space program by University of the Philippines in the OST. When I am actually answering the rejoinders for the OST, it felt like the project will actually have deep connection with the real world quantum applications. So for example, optimizing energy systems, modeling climate behavior, which rely heavily on space-derived data. To guide the presentation, since the Philippines is from the Pacific Ring of Fire, I will like to use metaphors in my presentation. A volcano. For a volcano, the innovation builds quietly beneath the surface through data and collaboration until it erupts into real impact. Planning where to place electric vehicle charging stations and solar energy systems is complicated. On the surface, the Philippine map reveals hidden challenges. So if you have your Google Maps, this is what it reveals to you. But underlying these maps, or on the surface, you have maps of roads, buildings, and existing grids. But at the surface level, but there are deeper problems with representing these maps. There are flooding that happens, which area have low solar potential, and how people actually move and use the energy. So these issues are connected to, number one, urbanization, disasters, energy demand, and the costs can't be solved one at a time. It should be solved collectively. Planning electric vehicle and renewable energy infrastructure requires going beyond what maps can show us alone. We need tools that help us understand the layers beneath so we can plan smarter from ground up. So our approach is to uncover what's hidden. We use main tools, our tools beneath the surface, remote sensing and GIS to see patterns in land use, weather, and risk. Artificial intelligence to forecast things like traffic, solar output, and demand.
finally, quantum algorithms to actually solve planning problems with many variables and constraints. These tools work together like magma in a volcano, pushing upward to support better data-driven decisions above ground. At the heart of our project is what we call the innovation engine. This innovation engine has 3 layers. Number 1, space data fusion layer, combining satellite and local data. Second, quantum optimization core, finding the best locations and configurations. And finally, AI forecasting engine, predicting solar performance, load patterns, and disaster impact. Just like a volcano, it has pressure and energy deep below. This system builds knowledge and supports future infrastructure. Our implementation strategy is simple. We organize the project into 3 years. Year 1 is to collect data, electric vehicle usage, grid capacity, solar readings, and flood zones. Year 2 builds and tests models using AI and quantum tools. And finally, Year 3 delivers planning tools such as maps, forecasts, and optimization kits for LGU and partners. At each step, we work with local groups to make sure our tools are useful, timely, and realistic. The project has just finished its year 1, quarter 1. So I will not be presenting any results yet. But our expected contribution lies with the outputs like research papers, models, and planning tools. Broader impact that are tools that help energy agencies, disaster planners, and urban managers. And finally, collaborations such as training sessions, student involvement, and memorandum of agreements and understanding with cooperatives and local government units. Like a volcano's eruption spreads minerals and nutrients, we hope these outputs will support future planning and development. All right, let me continue. Yeah, so for the project, Project Stark is part of the Philippine-Thailand Ideal Program. So I'm asking how this PH Thailand Ideal Program came into what it is right now. It is actually part of what happened in the discussions of the Philippines with Thailand counterpart, and QCSP is actually one of the prime movers of this call. We were just lucky because we're the only one who submitted the proposal, so probably that's why we get it. But our goal is really to create a working environment that can help Philippine communities make better decisions about electric vehicle and renewable energy infrastructure. Infrastructure. We use real-world data that is from local weather, disasters, and demand profiles to make sure the system fits our context. Our team is handled by a diverse team, engineers, researchers, and planners from Adamson University. We even take in architecture practitioners just for us to have an idea on how are we going to plan it out in the future. So experts in quantum computing, AI, renewable energy, architecture, and systems engineering with supports research staff and student researchers across different disciplines. Each person brings a skill that helps make the project complete and grounded in reality. Collaboration as part of the Philippine-Thailand program is also very important. Adamson University, together with our previous speaker from Suranari University of Technology, and also Quantum Computing Society of the Philippines, are working together to advance quantum technologies for practical use in electric vehicle and renewable energy planning. This collaboration focuses on, number 1, cross-compatibility of planning systems developed across institutions. We understand that what might work for the Philippines might not work for Thailand and vice versa, and also in different places in the world. Number 2, resource sharing. Adamson University houses high-performance computer infrastructure, while Suranari University of Technology has quantum hardware. We would like to make use of those resources so that we can achieve the goals of the project. Finally, knowledge exchange on quantum computing, understanding local e-vehicle markets, and applied technologies. By connecting these academic institutions and technical societies, this partnership fosters a shared ecosystem for innovation in quantum simulation, measurement, and decision support system. Of course, just like TIP's project, we actually have a technology roadmap that would support how will the use of quantum technology evolves through this application. From 2025 to 2027, we would like to build our core system and test our early models, expecting TRL level 3 as an output. From 2028 to 2029, we would like to let our local government units and agencies use early versions of the output of the project, leading towards TRL 4 and TRL 5. And finally, from 2030 and beyond, we would like to do wider rollout to national and regional levels, focusing on TRL 6. That is provided that the OST Preserved will still support it after the project finished. Each year builds on the last, like a volcano layer, forming slowly before the powerful release. So currently, so far, we have finalized our core team. We also have met with our local international partners. We also started collecting and organizing data for our AI and quantum training. We're now working on early prototypes like solar prediction and risk maps for our local government unit stakeholder to test with our collaborators soon. So way forward, we are actually laying the foundation for an integrated planning system using space data, artificial intelligence, and quantum methods. We would like to also do strong partnerships with local government units, academe, and industry, which are already in place as of the moment, but we would like to partner with more. Quantum algorithms, based on what we have seen, show promise in addressing the complex challenges of energy distribution and infrastructure planning. After the end of the project, we would like to prove that this really is promising. And our next step is to include testing the tools for local communities, improving their performance, and preparing for wider regional deployment. Looking ahead, we aim to tackle additional challenges like disaster-aware planning, inclusive mobility, and cross-border energy strategies. We actually invite your continued support and collaboration as we grow this initiative into a working solution. That's one that rises from the deep of innovation to real-world impact. Yeah, so as I close, I would like to end and echo what the spirit of our Thai counterparts' message. They said in the last presentation to create one and use in many. For us, it is build one and empower many. If we would be able to get the goals of the project, that's one step in building one. And we would like to empower more people to use quantum technologies and maximize this use for its application. Thank you very much.
All right, thank you, Dr. Purio. So I'll like to request to stay on the stage, and for all of the previous speakers, we will be sitting here on the couch, right here, for you to answer some questions from the audience. So for those who have questions, you can queue up to the mic stands there. I know we're almost close to the coffee break, but please hold on a bit. These will be very key insights for those aspiring researchers and those who wants to go forward with developing, further topics in the Philippines. So yeah, please be comfy. Please take a seat, guys. Again, take a seat. Yeah. Please take a seat. Dr. Apolinario, Dr. Dingel, Doc Tess, Ross. So we can sit down like friends, you know. So right, oh yeah, we have already one question on queue. Andrew Koenig has a question. Yes, please.
Thank you for Professor Bingle. You said that behavioral psychology is an important ingredient in quantum. Could you explain a little bit more why you think that?
So in Philippine setting, I believe that one of the key portion in trying to change the mindset of the Filipinos, in trying to improve not only in technology, but also in the behavioral side. As a scientist, I think innovation consists of two things, technical innovation and behavioral innovation in order to grow. Right now, we don't consider psychology as an agent of change for Filipino, for our. But I do believe that it is necessary. I might be wrong, but that's how I
Love it.
look
Thank
at
you.
it.
Right. Yes, please.
Good morning, sir. Good morning to our speakers. I have a few questions here prepared. First is, how are data encoded into qubits? Second is, how are quantum circuits created? Third is, you may answer the first two.
I'm sorry. The first question is.
My first question is, how are data that we've collected encoded into qubits so that we could run it in the quantum algorithms?
Okay, so this is directed to which of our...
anyone could answer.
Anyone, okay. Yeah, Bib Ross.
Okay, so I would like to answer from a quantum image representation point of view, since I am working on a quantum image project. So in a classical sense, we encode our data into bits. No? So like 00 represents this thing, 01 represents this thing. No? So we use the similar idea as qubits. No? So for an image, so we have an image, these pixels. The pixels are encoded as qubits. No? So pixels have position information and color information. No? So we use a quantum state for color, we use a quantum state for position. So that is how we encode the qubits in a quantum image perspective.
Okay. And for the next question,
Second is, how are quantum circuits created?
Quantum circuits created. Okay, who wants to take the...
Although I haven't created a quantum circuit, but I think it's very similar to how you do like semiconductor circuits. So if you're familiar with a transistor, for example, you start with a substrate. So you start with silicon, and then you pattern the substrate to define where your drain, your source, your gate regions are going to be, and then you dope certain regions so that you have a certain electrical property for that material. So it's very similar. Now that we're trying to go into a photonic structure, so it's the same thing. So we have to choose a substrate, and then we look at what structures will make up a photonic integrated circuit. So what does a waveguide look like? What material should be used? But it's really a process of patterning, deposition, and etching in different orders depending on the target structure.
Next is, how do we know how many qubits are we going to use for a specific project or for us to run a quantum algorithm?
I think Dr. Apolinar has insights, but I think, yeah, please go.
Okay, could you repeat the question? How many qubits?
Yes.
Okay. For a certain algorithm. It highly depends on the type of modeling that you would be doing. So for a quadratic unconstrained binary optimization problem, which in our case that would be what we would be doing. So we'll take into consideration, for example, for a given power grid, if you consider 1,000 buses, then for 1,000 buses, you consider, let's say, 6 binary features. Those 6 binary features, you multiply that by 2, so that would be approximately 12,000 binary value. then you just look at it in terms of the raise of the power of 2 to know the number of qubits that we consider. So for instance, we consider 2 to the 3, it means you have 8 qubits, and 8 qubits, it means you have this possible number of combinations.
So I'd like to channel that to Ross as well. I think there's a different criteria for determining qubit numbers or qubit size for images. So it's a case-to-case basis, I guess, for Kubo-based problems like optimization. But what are your views on, for example, fixed types like image processing?
Okay, so my background is quite different from my colleagues here. So I come from a computational background. No? So I just look at the math. So when determining the number of qubits, you usually do some complexity analysis. No? So from there, a lot of the work that has been done comes from complexity analysis. Then from there, you can derive how many number of qubits is approximately needed for a certain algorithm.
So before we go to the next questions, I'd like to pose this as for those who are planning to do proposals. So for our speakers, how important is it to have multi-stakeholder views on your research? And how would that form differently in probably your roadmap or your project development or even your output? So anyone could start.
I think it's very important on the aspect that you would like to have takers. I mean, of course, we learned in the past 2 days that we're not just doing quantum just because it's cool, it's fun, it's complicated. We're doing it because we felt like it has applications that can solve problems that are not solved yet. So having important stakeholders who can take in your projects later on is very, very important. In the context of, for example, the OSTP shared applications, they would like to see not only the technical feasibility of your study, but also if your study, if the research finish and the output or expected outputs are done, who will be the takers of those projects?
So we have only 1 minute left, so I think we can have very few questions. One quick question for our gentleman here.
All right, so thank you. So as I've been hearing about, I'm actually planning to consider quantum as part of, say, a master's thesis. So what are usually the realistic timeframes of researches in quantum computing, say on algorithms or any for that matter?
Anyone who, is it directed to any one of our speakers? Anyone who would like to take the question?
Okay, I'll just base this on my experience, so I'm not sure what would be the answer of the other members. You could not actually gauge how long or how fast you would be needing to understand quantum mechanics, quantum computing, etc. That's why when my advisor told me to include that in my dissertation, at the back of my mind, I was thinking I need to have a reason not to do it. Because I know that as of this point in time, quantum computing is very new. This has been emphasized in all of the talks since Wednesday. So, but at the end of the day, you would be still going on whether are you willing to take the risk? Are you willing to enjoy the struggles in understanding quantum mechanics or the struggles in identifying what type of quantum algorithm you would be using for your thesis? So it's more on a personal take for my case.
I think the safest answer depends on your supervisor.
I think I can add to that. On the perspective of what input you would like to put on your quantum algorithms that you are to develop. In the field, when I was studying in Japan, data is very, parang maraming data. There are lots of data in Japan, and some of them are grid-based data that you can just go to the pupunta ka lang sa, you will go to the town hall, you will ask for the data, and they will give it to you. It is also important to understand what kind and types of data you will be feeding to your algorithms, because that will also add to the time frame. For example, if data is not yet available, you would like to make sure that you have like counterparts of those data that might be useful for your algorithms.
Right, thank you. So I'm sorry for those who are still in queue. I believe we have a break, so our speakers will be here until the afternoon anyway, so you can ask them. I guess, if you have any specific questions, especially for those who have questions on how the grant proposals were written, I think that's something that our speakers would like to discuss with you later on. So thank you guys, and have a wonderful break, and thank you.
May we request the speakers and the moderator to stay on the stage for the photo documentation. Calling all the documentation team to take pictures for the fireside chat or fireside discussion. Okay, thank you so much once again to our research speakers, Mr. Ross Mariano, Dr. Maria Teresa de Leon, Dr. Benjamin B. Dingle, Dr. Gerard Francesco Apolinario, and Dr. Mark Angelo Purio, and to our moderator, Mr. Dylan Josh Lopez, for an informative and meaningful session. Our next series of presentations will highlight quantum science and research in the Southeast Asia region. And to moderate this session, let us welcome on stage Associate Professor Nolene N. De Jesus.
All right. Thank you very much to our previous speakers for sharing the updates on quantum research here in the Philippines. This time, we'll take a look at what's happening across Southeast Asia, and in this session, we'll hear from speakers from Vietnam, Singapore, Thailand, and Malaysia. Some of our speakers were already with us yesterday. And for the first one in this session, we have Dr. Hung Kyu Nguyen, who yesterday shared Vietnam's Indo-Pacific quantum strategies and ecosystem. Today, he'll focus on the research developments happening in their country. Dr. Hung, the floor is yours.
All right. Thank you very much. I feel very humbled to be here again. Can I have a slide? Okay, great. So it's, again, a very difficult job for me to represent the research in Vietnam. Let's try. So as a country, we definitely have some certain amount of research in science and technology. For the most part of the research, it is mostly basic research. So we have it spans like across all fields: humanity, natural science, biology, physics, chemistry, etc. And it can divide by, like, we have a deep root, like 100 years ago, back to the colony time with the French people. And then with the world, most of our, let's say, our previous generation, they were trained in Russia. And then now, there is a new generation who are trained mostly in the US and Western country, who do like basic science. So I would say our generation, I myself got a PhD from the US, like carry on the mission in basic science. So we have a few tens of university who are focused deeply on research, which means like the professor there has to do research, has to apply for funding, has to carry on all the standard mission. And then we also have National Research Institute. we also have quite a lot of researchers worldwide. For example, we got one field prize recently in 2010 from Professor Ngô Bảo Châu, who graduated from France. But then I would have to comment that the private sector has not been so good. So when we talk about quantum research, we first have to look at the research in physics, and definitely we have a lot of we have the research span all field in physics, from high energy physics to condensed matter to biophysics to astrophysics. We have a special Institute of Physics, which is like mostly focused on theoretical research. We also have some fancy equipment, for example, like an accelerator for us to do some high energy physics. We have quite a few of institutions who perform graduate training, PhD level, master level across all fields of physics. And among them, we also have national prize on basic science. For example, the Taekwondo prize, the prize on applied science, on applied physics. And also we have also a special prize for women in science. And that has been like for, I don't know, 20 or more years. We recently we have a national program to promote research in physics, and it has been running for 10 years now. We have a special dedicated grant for people who want to develop new and modern subject in physics. So in terms of quantum research in Vietnam, we definitely have quite a few of people who perform quantum research. For example, in our university, there was a professor who do quantum gravity, especially in anti-de Sitter conformal theory. There are also people who perform specific quantum algorithm, similar to the one that you have heard from the Philippine researcher just now. We also have the third line professor from the Institute of Physics. He performed quantum entangled protocol, and he was actually back to this slide. The prize, the Taekwondo prize in the basic science was actually the first prize of all, was given to him as a remark for his contribution in quantum science. And so we have a full range of quantum optic, communication, PQC, QKD, and many research like that. So specifically, and then to narrow even more, what do we do at Vietnam National University at the Institute for Quantum Technologies? So here we have two main missions. One main mission is that we're going to focus on superconducting quantum device. We are building a lab there, and hopefully we can go to 10 milli-K very soon. We also have a lot of, and then the second mission is to gather all people in quantum technology, including quantum computation, algorithms, quantum chemistry, quantum foundation, together as a unique body to study quantum physics. We have a lot of collaboration worldwide. Specifically, we are in close collaboration with the best university in Japan, the University of Tokyo, and also Tohoku as well. We're going to have our first degree in master. We're going to have a very first degree in quantum communication, in a master degree, and we're going to opened it this October. I believe this is the first one in Vietnam in quantum technology. So we're going to teach there a lot about QKD, about quantum optics, etc. We have close collaboration with many other country, institutes in the world for KIT, for example, from Karlsruhe with Professor Alexei Ustinov, for example, in Grenoble, in Copenhagen, and many other places, in Singapore, of course. So what we do there, so in my line of research, the last two lines were the research in our group, in my group. So we do people from two kind of two lines of research. One is that we use quantum computation as a tool to study physics. I'm gonna go deeper in the next slide. And the second one is that we have some quantum machine learning study using QAOA, VQE, quantum neural network, etc. So here's a few research that I myself in our group performed. One of them is, for example, it comes from the observation that the quantum computer is actually a very nice machine to study physics. So if you're familiar with the quantum circuit language, you can see here that, like, for example, a Mach-Zehnder interferometer, this graph. So the Mach-Zehnder interferometer is actually can very conveniently represent using quantum circuit language with the Hadamard C0 and Hadamard gate. So it is a very, very simple tool. So as you can see, like previously, we have to build an experimental complicated setup in order to represent a Mach-Zehnder interferometer. But now we can run this thing very easily, either using, for example, IBM machine or any optical machine very easily. So we got a paper on this one, but then after that, because I am a physicist, so actually I always think in terms of physics. So what do we learn from that Mach-Zehnder interferometer? One example is that we can expand it to the Hardy nano-quality study, where, as you can see, the quantum circuit for the figure on the right-hand side is actually very simple. It's just a series of Hadamard gate, which is represented as a rotation gate, and then a change of C0. And here I show it as a Toffoli gate. You can easily extend this one to like any arbitrary number of qubits. And okay, we might not be able to run this one conveniently on the real device, but this way of thinking provides us a new intuition to study Hardy nano-quality. And it is totally symmetric like this. We performed it on the IBM Nairobi or Quito a few years back. The arrow doesn't look very nice, right? The precision is not so nice, but that's not the point. The point is that we can totally use this kind of machine to study something very fundamental, like the Hardy nano-quality. The other work that I want to point out is a picture on the left, where we really use punch package in IBM machine to redesign, to re-engineer the qubit into a Q-treat system. And when we have a Q-treat system, then we can represent the three neutrino flavor, electron, muon, and tauon, as a Q-treat. And then we let the Q-treat to evolve in the Hilbert space, and we can totally represent neutrino oscillation using a Q-treat. And everything is done on the quantum cloud. So that is a point that I want to point out here. And with that, I would like to stop my sharing about the research in quantum in Vietnam. And thank you for your attention.
Thank you very much, Dr. Hung, for sharing with us the research development in Vietnam. Let's give Dr. Hung again a well-deserved warm of applause. Next, we go to Singapore. Our next speaker is Dr. Suen Wei Yep. He holds a PhD in Quantum Information and Computing from the Center for Quantum Technologies, CQT, in Singapore. With a research background in developing quantum-inspired algorithms for logistics optimization, Dr. Wei Yep brings both technical knowledge and a practical view of how quantum can be applied in the real world. He is currently the Scientific Project Coordinator at the Singapore National Quantum Computing Hub, where he leads talent development efforts and works to connect research with industry. His work supports collaboration and explores real use cases of quantum computing in Singapore's growing quantum ecosystem. Ladies and gentlemen, let's all welcome Dr. Suen Wei Yip.
Thanks. Hello. Thanks for the introduction. Thank you, Philippines, for having me. So today, as opposed to a very specific research topic, I want to talk a little bit on a more broad sense of what we are doing in Singapore. So the title of my slides are as straightforward as it can get, right? This would be the overview that you see. Everything I will talk about will come back to this slide, basically. So in Singapore, we have a full stack quantum effort ranging from hardware, middleware, and applications, and it's vastly supported by the outreach and talent development, which I'm also part of, and a lot of industry and international collaboration as well. So on the hardware, the timeline of our development for our own quantum computing facilities in Singapore is what you can see here. So I just want to highlight that a lot of times were actually spent on the electronics development and the laboratory setup, right? So only recently that we are able to start doing benchmarking and calibration. So I guess the message that I'm trying to impart here is that building quantum computing facilities is actually very hard. So I admire a lot of the companies that are doing it successfully more now. So as you probably have seen from the pictures, the first quantum computing facilities in Singapore is a superconducting qubit 1, and currently we have a 1 dilution fridge hosted in Center for Quantum Technologies, CQT. These are the specs inside, and what I want to show more is the chips that are currently inside. We are hosting 2 chips. The first one is the IQM 5 qubit, and these are some of the specs that we have over the last few quarters these are the specs of the different qubits that we have characterized. And the other one that actually we are focusing a lot more attention on is, actually, by the way, just a quick fun fact that I think this chip is fairly old. It has degraded a little bit. I think now there's only 4. But the one that we are focusing a lot more attention on is actually the 20 qubit chip, which we only managed to characterize a lot recently, as you can see here. Currently, the T1 and T2 are as listed, and we are quite happy that the mean 1 qubit gate fidelity is above 99 for all of the qubits, and we are slowly characterizing the 2 qubit gate fidelities. Right now, it's still about 96 for the 5 pairs that we have done. We are still going to do a little bit more. And yeah, this is again, just to show you the 1 qubit fidelity. And other than the single qubit gate, 2 qubit gate, T1 and T2 characterization, we have also done a few benchmark tests on our system. The first one is we have a parallel CHSH violation on 5 pairs. We like this because it shows that our machine is actually quantum. In fact, when IBM first had their 5 qubit chip many years ago, our director, Jose Ignacio, was actually one of the first few people that went to do Bell tests and Mermin tests on their chips. And IBM did very well, according to his paper. So, yeah. So we also did a Mermin inequality test for 5 qubits, up to 5 qubits. And currently, We are generating as long of a GZ state as we can, up to 7 for now. We are going further and further. Hopefully, we can get above 10. So, we believe that. So, I want to pause here and say that these are kind of like the benchmarking efforts that we are looking to collaborate with a lot of different scientists around the world with, even companies. As you will see shortly later, there are some companies that are working with us to do all these kind of efforts, right? One last quote-unquote benchmark that we are doing is data re-uploading with a single qubit. So the idea is to learn the curve of the blue curve and then try to predict it. And what we get was the red curve. And yeah. And so yeah, like I said, Singapore adopts a very collaborative framework, and these are just some of the companies that we are working with. We are working with Keysight on a lot of the control electronics that is being used in our system. We are working with Rigetti to maybe do some benchmarking of chips, and Maybell is a dilution refrigerator. As the system grows, we need redundancy in dilution refrigeration. And QuantScience is also another chip companies that we are working with. Entropica will be on quantum error correction, and Quandela will be on Kibo. So just a quick note that there are a few more upcoming efforts in Singapore on the hardware front. One of it is Singapore and Quantinuum signed an MOU to bring their machine into Singapore. Hopefully that will not only benefit Singapore, but also the region here as well, right? So, and additionally, if you see on my first slide, I did mention more than just superconducting qubit on the hardware side of things. We are also developing our own neutral atom array and trap ion processors. And the last thing that I actually added, but I didn't send it to the organizers, is we are also trying to fabricate our own superconducting qubit chip locally. And also, of all this quantum hardware effort, I also want to give a quick shout out to Yvonne Gao's group, who's also doing a lot of good work on superconducting qubit. Her PhD student Clara is here if you want to talk to them. So next is on the middleware. The middleware platform connects basically the users to the hardware and translate whatever the user codes into signals and instructions to the hardware, right? That's the idea of the middleware. And in Singapore, we adopted the open source end-to-end middleware that is Kibo. And this is also another area that we are really very open for collaboration, because number one, this is open source. Number two, you can share your work, because it's open source, so everyone can use what has been developed by other collaborators to speed up your own development, right? A lot of these control electronic drivers, for example, Kibo supports quantum machines, zero instrument, now Keysight and Q-blocks, right? So, and this is an overview of what kind of packages Kibo supports. You have tools for simulation, you have tools for laboratory, like the hardware level control, and then you also have applications that are specialized in different areas, right? So Kibo, again, and these are some of the benchmarking studies done with the Kibo library packages on tensor network, and also some of the state vector simulation. You can see Kibo is actually doing quite well. And these are more kind of like Kibo Lab, where we use it for calibration and characterization, and here are some of the calibration routines and how some of the results that we have performed. And so there's one. Okay, so I missed one slide. So I want to highlight that the Kibo is. There are a lot of collaborators around the world that work with us on Kibo, and this is, like I said, when I told Aria, it sounds like I'm selling Kibo, but the idea is Kibo is actually an open source end-to-end, and we really want to work with more people to develop this, because let's be honest, this is the only way we can compete with giants like IBM, Quantinuum when it comes to middleware development, right? So, and this is kind of also the only way that we can use something to access our own hardware developed in various different universities. So Kibo can also be used to access the TII's quantum computer in Abu Dhabi. Yeah. So next, quick one to go into applications. So The application framework of collaboration in Singapore can be seen here, right? We want to combine the Singapore's ecosystem, which is where I'm from, quantum companies, and the non-quantum domain experts, right? So, and personally, from our side, what we are trying to push for is the dark blue area where we can foster a lot of collaborations. Obviously, whatever the quantum companies and the other companies work on, we have no control over. It's a free market out there, right? So for us, we focus on the dark blue area where we try to strike different collaborations in different areas to study quantum computing, whether it's applications or hardware or software, right? And in terms of what are the areas that we are looking to work on, these are the 4 different types of areas and some of the example projects that the ecosystem is working on. Okay. And before I end, I want to highlight again that today what I'm here to share is mainly to drive collaborations within the region. So this is the slide I was looking for. As you can see, one of the collaboration areas that we really want to drive is on middleware and algorithms development through Kibo. And these are the other countries and also institutions that are working with us on Kibo. NVIDIA is also one of them if you look there. Okay. And the other thing that we can collaborate on is actually on education. So we have a platform called the Q Talent platform that anyone can sign up and register. It's free. We have some of the best speakers around the world talking about the topics that are heavily specialized in. For example, our course on measurement-based quantum computing is taught by Robert Rausendorf, the person who created the field itself. Right? Lastly, there's also we are also hosting a lot of our visitors and students to our quantum computer facilities to discuss different ways we can collaborate and to talk and to look at some of the things that we are working on. So if any of you are somehow in Singapore, feel free to just hit me up. And last but not least, I just want to highlight that Singapore, again, is very open to work together with different countries to drive the talent up in this region. So we have a national quantum scholarship scheme. You can talk to me for a little bit more of information, but generally this is a bondless scholarship with very attractive stipend for quantum computing. So I think I will end with this. Time's up. Okay.
Thank you so much, Dr. Rief, for that very informative talk on Singapore quantum efforts. Also, returning today is Dr. Arya Shanchari, who yesterday shared about quantum grassroots development in the Indo-Pacific region. Today, she continues by giving us a closer look at Thailand's quantum science and research efforts. Let's give a warm-up welcome to Dr. Arya Shanchari.
Okay. See you again. Thank you for everyone to still be here before the lunchtime. Yesterday I was talking about how we build the community, right? And then how we go from scratch, like building people and connect people together to do research. And then today I will try to go like an overview of what we have done in terms of research. There are a lot of them, so I'm going to pick just one thing, a few things that I think it's really important. So here's a picture of many of us, and the next slide. What I'm gonna do? Oh, not this one. Yeah. So this one is a picture of the country, and you can see a lot of university logos there. So you can see that there are many universities from north to the south, and many of the universities are doing different platforms. And we could say that we have a lot of qubits in the country. It's different platforms. And the thing is, because we don't have much money, we cannot just buy IQM in Singapore, or just work with Continuum and buy a neutral atoms computer. So we are doing the different strategy. Is doing from the kind of the bottom again, trying to build a really small scale qubit from different platforms as possible, because we have a lot of students that came from abroad and then with like different expertise. So we have a lot of publications and also the prototypes, and I'm going to talk about something that most important. And we do across like 3 different areas with metrology, communication, and simulation. So let's start with the first one. I think this one is like, I think it's the most exciting one. And I think many people know atomic clock, right? I think atomic clock has been used quite a lot now, like cesium atom. So use like atom to do a really precise clock, because like cesium atom has like really precise energy level. And then you can use that to sync the laser, and then use the laser to do like a clock tick. So cesium atom is the old version now. And I think like the next version would be the atomic clock that made by like ytterbium, for example. There are many other atoms as well, but I think this one is one of the promising one. So it's ytterbium ion actually. So it's a ytterbium 171 plus. And then they can trap the ytterbium in the vacuum chamber. And in order to trap one, it's actually really hard. And once you can trap one ion, you can use that to sync the laser to do the atomic clock. So the atomic clock is used in so many areas, for example, like the time precision in GPS and so on. So this is one of the experiment in the National Institute of Metrology in Thailand. So like similar to the NIST in the US. Okay, so another one is also in the metrology side is the NV Center. I think many people, I haven't heard anyone saying anything about the NV Center yet. So we have the NV Center lab in Thailand. And so basically the idea, it works in, like you know diamond is the carbon lattice. And so if you take the one carbon, or actually 2 carbons out, and then leave one as a vacancy, and then another one replaced with the nitrogen. And somehow this nitrogen and vacancy is combined, electron is combined together somehow, and then make like a 2-level, like really nice energy levels. And then you can use that as a qubit as well. So this qubit is, can be run in the room temperature, and this is the thing. So our plan is actually trying to come up with maybe we could build a startup company and then make what is that called? The quantum computer with like 2 or 3 qubits to compete with like SpinQ, for example, as a educational purpose. So we are working on the NV Center. Already we got the result of like probing that there is a qubit there, and then we are working on like driving the qubit with a Rabi oscillation, basically to control. Okay, so now it goes on to the next one, which is the quantum communication. We also have a lab that worked on like optical qubits, and they are working on like entangled photons or single photon or even the QKD. So the QKD in the lab that we have in Thailand, it will be the QKD that based on the polarization, like the horizontal and vertical polarization QKD. And so the plan is to kind of, like we plan ahead in the sense that we want to build something called quantum network. I'm not sure how far we can go in that direction, but let's dream it. So we start with generating the QKD on the optical table. And then once we have the QKD on the optical table, then we can extend to the QKD across the province. And then hopefully at some point we can do the QKD through the satellite, like similar to the one that China has been doing quite a lot in experiment. Okay, so that is kind of the diagram of people who plan on the quantum network. And I think there's like a lot of typo with the last letter. I'm not sure why. So there are like many different universities that work together generating the QKD, trying to make the single photon source as better as possible. There's like a theory trying to work on like the HBN fabrication to try to come up with a better single photon source. And also there's one part that trying to build the photonic chip. And I heard like a lot of Philippines universities and labs that work on photonic chips, and that's like amazing. Maybe we could do something together. And the third one, and the simulations and algorithm. So this one is more on the different qubit, which is the neutral atom. So neutral atom, there's no ion in there, so it's just like an atom with no charge. And in order to trap the neutral atom, you will need the laser. So right now, they have done trap the rubidium cloud in the MOT, which is like the mod. And then right now they are thinking of doing the, what is it called, like the squeezer, the optical squeezer, to be able to trap each of the atom and then hopefully move around into a different traps. And that will be used for quantum simulation in the future. And those are the experiments. And we have a few groups that work on the theory as well. I'm actually one of them. I can't talk much about this, but basically it's related to the quantum machine learning. Come up with the algorithms that work on how to combine the machine learning with like the quantum circuit, and how can you do the quantum circuit in a variational way in order to like learn something useful. What is that? Wait. That is the, here. So the last slide of my talk, this is like basically part of my work as I'm a theorist. So my work is related to characterize the noise in the quantum device. So I worked a lot with the quantum experiment, for example, superconducting qubit, NV center, and ion trap, and then understand what is going on in their system, and then make sure that maybe they can do a better measurements, like how to extract the information from the like randomness in the data in order to like extract the parameters in the system, or maybe you can do like a quantum error, kind of error correction or error mitigation from the system. Okay, I think that's kind of the overview. So that's it for my talk. Thank you.
All right. We appreciate your sharing, Dr. Arvia. And now, we move to our final speaker for this session from Malaysia. We're joined once again by Dr. Chung Pak Shen. Yesterday, he shared Malaysia's role in the Indo-Pacific quantum strategies and ecosystem. Today, he'll talk about ongoing research efforts in Malaysia. Let's all welcome again Dr. Chung Pak Shen.
Okay. So, yeah. So, very good afternoon, everyone. So, this is basically part 2 of my talk. I will just briefly talk about the quantum research in Malaysia. So, as you already know, since yesterday, basically Malaysia has kind of like 4 trusts. So, the first one will be on the quantum communication and security. So the one championing sort of like the QKD would be Prof. Jyoti, Prof. Shamsuri, and then Jasni. So they are all working in QKD. So in the past, if you notice one of the slides from yesterday, MIMOS, this year they have their MIMOS Quantum Day. So in the past, MIMOS has done some QKD in free space. So they are trying to revive it again. Then we also have some theories like Prof. Siti and later on you'll see as well, Dr. Day. They are working in open quantum systems. I'm I'm actually the student of Dr. Hishamuddin. So Hishamuddin, Nurisha, me, and Umay, basically we are sort of like a research group working in fundamentals of quantum theory. So we also have Prof. Vanajan from UM, who is doing quantum chemistry. And then, yeah, you have the only person doing superconducting qubits and the instrumentation, which is Dr. Yap. And then you have two people working in quantum humanities. You have already met Carissa yesterday. So yesterday, I was asked what is quantum humanity all about. So one of it is to look at the policies. Like for instance, Carissa and I and Amin, basically we try to look at Malaysia's energy transition roadmaps and then see where quantum technologies can come in. So this is supposedly one of the book chapters in the energy transition in Malaysia. So it's not published yet. So right now we are also trying to propose some projects with MIMOS. The first one is to look at some applications in quantum computing. The second one would be collaboration between 3 universities, UPM, UTM, and UNIMED. So basically it's Yap, Shamsuri, and Nurisha. So the three of us, the three of the groups, they are trying to revive the quantum communication and computing for encryption and quantum safe communications. So the next part is I'm trying to sort of like show you another aspects of what I'm doing in quantum humanity, which is on quantum arts. So this is a picture that I developed with my artists. So the reason why I try to do this is to basically try to sort of like humanize quantum tech. Throughout all the talks you have listened to until now, you always think about technologies, technologies, and technologies. So we are trying to sort of like communicate quantum technologies to non-scientists in a form that they are familiar with. So one of it is on art. If you know what it is, you basically can identify some of the quantum elements inside this picture. You can ask me later on. So another one will be from Carissa. So she's basically experts in writing narrations and stories. So this is some of her stories. We pick it up and then we try to put it into a narrative and then show it in during the World Quantum Day, for example. So yesterday I also mentioned about not quantum. So this is what we are doing. So essentially we are doing a workshop. So you can see Carissa is on the left, and then on the right would be Andrew. So Andrew is demonstrating Mach-Zehnder interferometers and showing how you can do artwork using quantum, basically your polarizers. I'm developing a card game called Quantum Pod, and then Carissa is developing sort of like role-play RPG kind of thing, whereby you have some storylines and then you go through some of the quantum technology, not to say quantum technology, but quantum theory kind of thinking. So this is a combination of our events of what we are doing in one of the workshops. And it's not just that. So yesterday, Arya asked me like, what kind of things that we can collaborate with. So I mentioned this, but probably Arya did not know. I basically work with Creative Lab from Thailand, together with the Institute of Fundamental Study from Naresuan University. So my game is about quantum teleportation. So we sort of like, so what I did was I sent my files to the Thailand site, And then we do a Zoom call, and then I teach them how to play it, and then they play it on their event. So from what I heard is that basically they printed out 6 sets, and then it was like full house. I don't know whether this is true or not because I was not there. And this is a picture between me and Robert playing the game. So just to answer some of the questions from yesterday as well, basically the question is about what kind of collaborations that we can do. So I sort of summarized a few points. So I mentioned about the similarities and differences. So if we want to collaborate, I think we should sort of like identify the similarities and what kind of common goals that we can work together with. And then I think we should start small. Of course, we can go from top-down approach, like you propose for some policy papers and like working between government and government. But if you want to have faster results, I think we can start small and try to do some bottom-up collaborations. We should be careful about the silo effects because usually scientists tend to work in their own research areas and without talking to each other. So I think we should be careful about that. And then I also mentioned that you can view this kind of quantum race as a race between each other, or it's a race between collaborative kind of race. So that would be more like a relay race. So lastly, I would like to point out that in a lot of emerging markets, we sort of ignore this group of people, early career researchers and young scientists. So I would like to post one of the statistics from Malaysia, for example. So this is taken from Minister of Higher Education, Graduate Tracer Study 2025 in April. So according to the report, Malaysia basically said that all the graduates from higher education, we reached like 87.5% getting employed. And then 35% of those being employed are working in jobs unrelated to their field of study. So if you look at the numbers, it seems optimistic. But if you do the calculations, like for instance, if you have 10,000 of graduates, based on the percentage alone, you have 8,750 of the graduates are being employed, and around 3,000 will be working in unrelated fields. So if you put the statistic in the other way around, it means that around half of your graduates are either unemployed or working in unrelated fields. So just imagine, for instance, if you try to train your quantum experts in 3 years or 5 years, and you basically, only half of them are working in quantum field. So this is not something that we want. So this is something that I think we should be careful about. So as I say, we need to be careful about the silo effects, and we should try to collaborate with each other, communicate with each other, and work with each other. So I have a few other slides left. This is basically, if you are not able to come to the Quantathon, this is the teams. So as you can see, we have a team of different nationalities. So you have Thailand, you have Singapore, you have Vietnam, you have Philippines and Malaysia. So these are the teams, as you can see. So they are working in 3 tracks, climate change, medical and healthcare, and renewable energy. So we have 6 teams. So these are the people that you should sort of like value because they are the champion in your country in collaborating between the Southeast Asia region. So that's all for me. Thank you.
Thank you very much again, Dr. Chung. At this point, may we invite our 4 distinguished speakers to join us on stage for an interactive discussion with the audience. So the floor is now open for question. So, while the audience is gathering their thoughts, I have a question here. As part of QCSP, we focus on grassroots engagement among our youth. So, in your experience, what is the best practices or successful strategies have you implemented in strengthening quantum awareness, education, or community building, especially among students or young researchers?
So I mean, the question is like, how do we do that, or?
The best practices or the successful strategies. So you can give example.
Okay, I think like I will just repeat what I said yesterday. I think the stronger thing, the most important thing is the collaboration between researchers and maybe industries. And then if you can talk to them and communicate with them, anything can happen.
All right, so thank you.
Any other?
Collaboration is definitely one of the key things. But the other thing I also want to say, start young. I think that's one of the things that often overlooked. I think you want to start very young. You know, Chris Ferry, for example, I think maybe that's too young, quantum for babies, but I would say the secondary school level, in Singapore, we have QCamp that's targeted to A-level students, high school students that, again, Clara, I keep saying her name, Clara organizes. So if you are interested in those kind of activities, you can also ask her. So start young, I would say.
All right, so I think we have a question from Sir Andre.
Thank you. You all have much bigger and more advanced individual programs than I knew about and expected. And there seems to be a lot of exchange and partnerships and so. But as an ignorant outsider, to me, I'm wondering, and somebody mentioned, yeah, we can't buy an IQM quantum computer, right, and do stuff. Why is there no real coalition between some of the ASEAN countries and quantum initiatives and join forces? Is that something that's being discussed, or is, I don't know, your history, politics?
I just want to say this is an excellent question, and I think this conference serves as a first step to it. I acknowledge your feedback in that sense, but I think we are working, this shows that we're actually working more towards that.
Okay, I think it's still because each of us are still growing, and I think it's not at the point yet that we can work together yet. It's just like we're starting to work together, but in the past 5 years, I think each of the countries that form what I can see now, we have been building the talent pool, like research and students and faculties. And hopefully in the next 5 years, that will be the good time that we can start working together. And that's why we have been talking about how can we organize something like a conference between the Southeast Asia and then bring like the scientists together, bring the industry together, and then see what we can do. We don't want to do in the sense that, let's say that the investor in Philippines wants to do something. They don't have to look inside Philippines. They can look into, I don't know, academic in Thailand, and investor in Thailand can look out in Southeast Asia as well. So it's kind of the trend right now in the next 5 years, I think. Thank you. Anyone?
Well, I just want to add a point that I kind of disagree with you in the sense that, let's say last year we have a summit in Thailand, and this year we have like now the event in Philippines, and by the end of the year it's going to be in Malaysia. So I think the way I see it is it's moving really fast, and I think that what you mentioned is going to be something naturally occur in the near future.
Hello, I think I have a follow-up question to what Andre just asked. Wade, you mentioned that Singapore is now collaborating with Continuum, and you mentioned very briefly that this would be very good for the region. Could you be more specific about how you think Singapore's hardware capabilities and resources that can go towards like hosting hardware in Singapore will benefit the region? Like what kind of collaborations, what kind of access is ASEAN going to benefit from that?
So this is a very tricky question because I can't speak on behalf of Continuum, but if I were to speculate, I think Arya has pointed out that maybe not every country can afford a Continuum machine themselves. So if if Quantinuum wants to penetrate the Southeast Asian market, I think one of the ways is to do it is that they maybe through Singapore they can work together with the other countries for access but again, I'm not speaking on behalf of Quantinuum, so and I think Leah is here. You can ask her.
and what about the NQCH hardware, the IQM chips that you all have?
So I guess it's a good time to mention that the IQM, we don't have an IQM system. We only have the chip, okay? Because again, we are not that rich, okay? But for that chip, the idea is that, as you can see, we are undergoing a lot of calibration and characterization effort. The goal has always been to slowly opening access up to more and more people. But I'm sure you agree that there's a difference between a few researchers accessing it, running some small circuit versus opening it up to the region. We need to make sure that things are done correctly. If not, it will look, we won't instill confidence when we do it next time.
Thank you.
My question kind of relates to that, if I may. Also on the hardware in Singapore, because you mentioned these different thrusts for the IQM chip. It seems you assembled the whole cryogenics stack yourself and doing all the testing. I wonder, and then you also seem to have efforts in 3 modalities to completely from the scratch build quantum computers in Singapore. I wonder if there is a kind of a strategy behind kind of where you're planning to go on this. We had these talks in the past days on kind of build, buy versus use. If there is a clear thrust, and also then in general, if you can share any learning already or any benefits that you incurred from that experience that may be valuable for other countries in the ASEAN region.
Yeah, that's a good question. I think the goal was always to build capabilities, right? I know there are some companies here, but I don't believe that we need sovereign solutions. That's number one. That's why I know that our chip is IQM, but we are also constantly fabricating our locally designed chips. This is to build, number one, to build capabilities. Number two, that to be frank, we don't want to be beholden to any private companies change of policies, because at the end of the day, they are free to do whatever they want. So this is also the mindset that we adopt when we adopt Kibo. And as far as the future is going in terms of different hardwares in Singapore, I think currently there's no winner in the quantum race in terms of different platforms. I know some people really like NV centers, but Singapore is trying to diversify its investment in trap ion and also neutral atom on top, and some photonics control electronics on top of a superconducting qubit. And just also to reiterate that the neutral atom and trap ion platform are built in-house. This will not be a chip that we buy somewhere else.
Okay, so I think we can accommodate one last final question.
Thank you. So Elizabeth Thomas-Reno from the OECD. For those of you who heard me the other day, we were talking about the work that we're doing on developing principles and thinking about sort of mission-oriented vision on the development of quantum technologies. And one of the ways we've chosen to do that is work with researchers and stakeholders early on. I'm interested to know to what extent that's part of the conversation that you're having when you're getting together. I think to the point of how can you sort of integrate your activities or find common projects to pursue. It's easier to do so when you have that common goal. I really hear missions in the projects that you're doing individually, and I'm just interested to know to what extent collectively you've covered that ground.
I think we are still at a very early stage in terms of what you have said. But I think last year when we organized the workshop to talk about how to work with each other and then how to, in the ASEAN context, how we can work together, we did propose, for instance, whether or not we can establish a subcommittee in ASEAN that specify on QT, for example. But I think eventually we try to sort of like delay that kind of process because it would take a lot of time, which is why just now I mentioned you have two approach of collaborations. One is top down, another is bottom up. Because, but like top down is kind of slow because you need to go through like all the regulations, all the negotiation, and all the processes. Like for instance, just for us to get the name ASEAN in the ASEAN Quantum Summit, it took us a year. Yeah, so that's how slow it is.
I guess just a quick follow-up. The point of the discussion at the researcher and stakeholder level is really to allow a little more space before a political or a bureaucratic construct can help. So to the extent that in your informal discussions, you're able to facilitate a bit of that flow and then go back and inform your politicos and others who are stuck in those longer processes. At least from our experiences, that's proven a way to make sure that the governments aren't operating blind or without some of those important considerations that otherwise end up as unintended consequences of their policy.
I can add a little bit that the C Hackathon, the Southeast Asia Hackathon, is actually one example. We got the support from the OQI, which is like part of the CERN in Europe, and they gave us money. And that's like one thing that we just need as a push to for us to combine at least 5 countries. Actually, we got Cambodia and Laos as well, but there are like a few students. And at the end, it was just like 5 countries, which is a lot already. And we are going to organize it this weekend. And that will be the first, I would say, like real ASEAN collaborations in the region. And we hope to see more of that in the future.
Congratulations.
Thank you. Yeah.
Okay, so unfortunately, due to time constraints, so this is the end of our session. Thank you very much for your insightful questions and engaging responses.
Thank you.
May I kindly request all the speakers to stay on stage for the photo op.
Calling all the documentation team to take a quick photo opportunity for the panel discussion.
We sincerely thank our distinguished speakers, Dr. Win Pok Hong, Dr. Sun Wei Yap, Dr. Arya Chantari, and Dr. Chong Pak Shen for their invaluable contribution, as well as our moderator, Dr. Nolin De Jesus, for expertly guiding today's insightful exchange of ideas.
So a quick announcement for all our attendees. If you are scheduled to check out at 12 noon, kindly proceed with your checkout and return for lunch afterward. So at this point, lunch is served, and as you enjoy your meal, we encourage you to take the opportunity to connect with fellow participants, share insights, and explore possible collaborations. Bon appetit, and see you later.
QISTCon.ph 2025 a reality.
On behalf of the organizing committee, we extend our heartfelt thanks to the International Year of Quantum and our esteemed partners for their unwavering support and collaboration in making QISTCon.ph 2025 a reality. Your feedback matters. As we continue to improve our services and programs, we invite all delegates to take a few moments to answer our customer satisfaction form. Your insights will help us serve you better. Scan the QR code to start. Thank you and enjoy your lunch. Your feedback matters. As we continue to improve our services and programs, we invite all delegates to take a few moments to answer our customer satisfaction form. Your insights will help us serve you better. Scan the QR code to start. Thank you and enjoy your lunch.